Good evening, all. We are connecting you from Oasis Institute of Technology, Pulivalam, Tiruchirappalli, Tamil Nadu, for this ATAL FDP on quantum computing and AI, a potentially transformative synergy for future India. In this third day, session 5, you are going to have a talk by Mr. R. Venkatesan, Senior Vice President and Head, Consulting and Delivery, Profinch Solutions Private Limited, Bangalore, Karnataka, India. He's going to talk on visualizing the role of quantum computers and AI in the Indian finance industry. A short note on R. Venkatesan.
AICD Training and Learning Academy sponsored faculty development program on quantum computing in AI. We welcome you all to this program. It's a potentially transforming synergy for future India, organized by our Oasis Institute of Technology, Pulivalam, Tiruchirappalli. We welcome to the day 3, and it's my pleasure to introduce Mr. R. Venkatesan, Senior Vice President and Head of Consulting and Delivery at Profinch Solutions Private Limited, Bangalore, Karnataka. Mr. Venkatesan has long, valuable industry experience and extensive background in the finance technology, consulting, and large-scale solution delivery. He has overseen complex digital transformation projects for leading financial institutions and has been instrumental in integrating advanced technologies into the banking and finance sector. Today, he will be speaking on visualizing the role of quantum computers and AI in the Indian finance industry. His perspectives will provide participants with a practical view of how quantum and AI could revolutionize the financial services domain in India. And I welcome Mr. Venkatesan. Thank you.
Hello. Can you all hear me?
Yes, you are audible.
Yes, sir.
Okay, thank you. To begin with, I want to thank the management of Oasis Institute of Technology and the coordinators and the respective team who have taken a lot of efforts to arrange these sessions. Okay. So I see this session as a very interesting meeting point of industry as well as academia. Okay, because from industry perspective, we always see academia as a front runners of technology. Okay, so while academic institutes work a lot on technologies, the point at which it comes to industry, okay, is the point at which it can actually add value to some of the industries. Okay, because for industry to adapt and adopt a technology, there is going to be a lot of investment of money. Okay, so if money has to be invested, there has to be returns as well. Okay. So if quantum computing has come to a point where industry is adopting the technology, it actually means it has come a lot of, it has covered a lot of distance in setting up the trend of latest technology. So thank you all once again for this opportunity. Okay. Now I'll go to my presentation. Can you all see my screen?
Yeah, your screen is visible, Mr. Venkatesan. Thank you.
Thank you. Okay. So I want to introduce the company for which I work to begin with. Okay, so I work for a company called Profinch Solutions. So we are in the industry for the past 10 years. So what we do is we work with financial institutions. We work with various banks, financial institutes, NBFCs, financial services agencies, credit agencies, central banks across the world. We help them in consulting engagements. We help them to trend, to uptrend the technologies that they are already on. And we also spread the best practices on which they should be working on. Okay. So we work on both aspects, technology upgrade as well as functional and business upgrade. We do both for various banks across the world. Okay. So to begin with, I want to set the expectation of what are we going to cover as part of finance industries. Okay. So while finance industry is a very generic term, we are going to speak specifically about some of these key players. Okay, so when I say key players, we're talking about banks. Banks can be a retail bank, a corporate bank, or a central bank. Okay, and investment houses. Okay, so those who work with the capital markets, those who work on stock trading, okay, and various other investment activities. Lenders, these are the new age players who only lend money. Okay, so they are the ones who lend money to other agencies. Okay, and even real estate finance. Okay, nowadays a lot of real estate finances companies also have come in. Okay, so they only do mortgages. Finance companies, non-banking finance companies who do not do banking operations but deal with money. Okay, and insurance companies. Okay, so we are covering the BFSI part of this as part of the financial services sector. Okay, so when we are going to talk about quantum computing, we are going to see the impact that it may have on some of these key players. The number of players and the quantum of change and the quantum of impact that quantum computing can have is massive. Okay, so we are going to see some of the specific cases for some of these players in this presentation. Okay, so how can quantum computing revolutionize the financial services industry? Okay, so there are two main reasons or two main aspects of quantum computing that interest any application developer or any startup companies or any institutions to adopt quantum computing. Okay, so one is the amount of data it can guzzle, okay, the amount of data it can process, and the speed in which it can process. Okay, so these two both, the both goes hand in hand. Okay, so because there are a lot of existing systems that can process a lot of data, but takes a good amount of time. Okay, so there is a classic case study during COVID onset, during the COVID-19 days. There were a lot of agencies who started to build different models to understand the impact of COVID on the economy. So when they tried, it took them 3-4 months to build a model. Okay, and when the model came out, it took them another 4-5 months to populate data and process the data and come up with a model of impact. Okay, so the model came out, the impact saying the economy is going to hit say 30 to 35%. Okay, but by the time the results were known, it was a good 8 to 9 months, and industry has already fallen by the economy has already fallen by 20%. Okay, so time is essence here. While there are a lot of systems that can process data, the one that can process data faster, okay, and give the insights faster is the need of the industry. Okay, so on these lines, there are these three angles that might interest any institution in the financial services industry to adopt quantum computing. Okay, so first one is the computational capabilities. Okay, because you will keep seeing this everywhere: financial simulation and modeling. Okay, what this is something that we will see down the line in the presentation. So financial simulation and modeling are some of the activities that requires plenty of time. Okay, because there are models that run for months together. Okay, there are models that run for days, weeks, months. Okay, there are all sort of combinations. So quantum computing can typically reduce the timeline of these activities. That's the first angle. The next one is the AI part. Okay, so right now, AI is everywhere. The artificial intelligence models, tools, agents are everywhere. Okay, they have become mainstay. While a lot of people talk about AI as an upcoming technology, it's already there. I mean, the fastest or adopted module of AI is the chatbots. If you look at a lot of chatbots can talk to you. Go to any website today. You go to ICICI Bank, HDFC, or ICICI Prudential Insurance, HDFC Insurance. You go to any of these insurance websites, you will see a chatbot present there. And the chatbot can talk to you in different languages. You can type in Tamil, Telugu, a lot of languages it can talk. It can do a lot of activities as well. There was a time, if you look at, say 2-3 years back, there was chatbots still. Okay, even chatbots are not new to the industry. There were chatbots, but typically it will communicate in a monologue. It will ask you for your name, your phone number, and it will ask you, what is that you want. Okay, so once you type that, it will record the information and it's going to pass it on to somebody else. It is going to pass it on to a human agent who will look at the data and call the customer and start discussing on why the customer went to a particular site. But today, the chatbots have crossed a lot of boundaries. It can chat in vernacular languages. It can chat with you in your native language. It can do operations like it can issue a policy. It has come that far. It can open an account. It can issue a policy. Okay, it can read your face. It can read your emotions. So a lot of advancements have come to AI that directly impacts the end customers. Okay, and typically, while AI we say is faster, AI also needs a lot of computational capabilities. It needs a lot of computing power, okay, to run what it wants to run. Okay, so like you must have seen a lot of AI models. Again, it runs for days and months. So quantum computing coming with a lot of processing power is going to help AI as well. The third one is a very important area that we have to focus on. So cyber attacks. Okay. So today, if you look at cyber attacks across the world, the most common target of cyber attack are the financial institutions because they handle money, right? I mean, even if you see the latest coin DCX breach hack, it was hacked and a lot of crypto assets were stolen. Okay. So financial institutions were always a target of the hackers and cyber attacks. So what quantum computing does here is on both sides. Okay, so quantum computing is more like a double-edged sword. While you talk about the advancements of quantum computing, it can hit industry in both ways, positive as well as negative. Okay. On the positive side, it gives a lot of computing power. On the negative side, the same computing power can be used to break some of the existing infrastructure. Okay, for example, cryptography. Today, the cryptography is based upon a simple fundamental, right? I mean, it's based upon the logic that to break a key, it's going to take years for somebody to break it. It's not that keys are unbreakable. If you're going to bring a supercomputer, it may break it in months or years. So every key can be broken. But imagine a computer, a quantum computer, if it can break the key in a matter of seconds or minutes. Okay. So it's going to put every data encrypted so far at risk. The magnitude is a bit different. It's not we are not talking about future cyber attacks here. What we're talking about is today, the biggest scam that's happening is a lot of hacking institutions and hackers today. They're hacking financial institutions and they're taking the dump of data. Okay. So they're taking the dump and they're just storing the data as such because they're waiting for the time at some point in time when we're going to have practical quantum computers and they can use the computers to decrypt the data and use it for their purpose. Okay. So at present, if you look at the world financial institution scenario, it's a bit bleak because a lot of incidents of data harvesting happening. Hackers just hack into a infrastructure, steal data and do nothing. Okay, so because if they at this point in time, they will not be able to use the data because these are properly encrypted, so they cannot use the data as such. But today they'll keep the data, and at some point in time, when they will have capable computers, they will decrypt and they will start using it. Okay. So cryptography and cyber attacks is an angle that is a bit negative in the sense, but see, it presents both sides. While it presents a negative scenario, it also gives you technologies to counter that, but still, this is one angle we have to be very careful about. Okay. So these are the three pillars of quantum. Okay, so quantum computing is one area of this. So the three pillars of quantum technology, if you look at, okay, so talk about quantum computing, quantum security, and quantum sensing. Okay, so these are the three pillars that can have an effect on the finance industry. So So at this point in time, quantum computing and quantum security has progressed a lot in terms of technologies. Quantum sensing is still at a very nascent stage, okay, because there are not a lot of use cases that justify the cost of adopting this technology. Okay. So let's look at an example of each of these and understand what each of these is meant to do. Okay. So quantum computing, we have been hearing a lot for the past 2 days about quantum computing, what it is, what it can do. So I'm not going to go detail into that. Quantum security is something that I just spoke about. Okay. The quantum cryptography, encryption, how we are going to tackle the effect of quantum technologies on encryption and cryptography. Okay. So there are terms like post-quantum cryptography. So these are cryptography technologies that will take you to the level of quantum. Okay, so that's why they call it as post-quantum cryptography. So if you move to a PQC standard today, It means tomorrow, even if a quantum computer is available, okay, your encryption is still safe. Then you have some more technologies like quantum key distribution and how do we distribute the key? Because again, encryption is all about a private and public key and the transmission of the keys. Okay, so quantum key distribution is a technology in which you can safely transmit a key in a unbreakable manner. It's something that cannot be hacked. Quantum random number generators, again, is a quantum algorithm. Okay, so it's a different way of generating a random number that cannot be hacked. So that, it's truly random, because at present, the current random generator algorithms can be hacked by quantum computers when they're available. Okay, so it's not going to be really random. But this QRNG solves the problem of having a truly random number generator. Quantum sensing. So quantum sensing is about measuring quantities. Okay, so the most important quantity that a finance industry, any industry may need, is a time. Okay, so for example, in terms of milliseconds, nanoseconds, it has to measure that exact time on which an event happens. So the use cases of this are not much in the industry. At least in the finance industry, we don't see a lot of use cases for this. There have been some case studies and some attempts to use this technology to see if they can do something. For example, if you look at the liquidity markets, so for example, today, take two central banks, okay, a Reserve Bank of India and say a monetary authority of Singapore bank, okay, and there is another third-party bank. Today, if money has to move from one bank to another, and if one bank has to borrow from somebody else, so they go to the market, they borrow, and they return after some time. Okay, so the next day it returns the money back to the market. This is called overnight money, and these are in the market, these are present as money market institutions, treasury bills. A lot of instruments are available in the market. So the interest is always computed from the time you take the money and the time you return. Okay, so the time of interest is always computed this way. And when you talk about billions of dollars and millions of dollars, every minute matters. Okay, so there was actually a case study. We'll see it a bit later in the presentation. There's actually a case study in which two banks did this liquidity analysis using quantum sensing algorithms and the exact time. And they found that the savings has been millions of dollars because of the huge amount of money involved. So there has been some case studies already in these technologies and in these areas. We will see some of the case studies down the line. Okay, so while we spoke about a lot of case studies and use cases for finance industries, the consulting companies have come up with different use case impact. Okay, so we're talking about, okay, now what business value does these use cases bring in? Okay, so if you look at 8 and 11, okay, so these are seen as very high possible use cases, very high business value use cases. Like I said, right, encryption and cryptography. And the next one, if you see the very high business value, it is you'll see 4 and 1, okay, currency trading and credit card payment fraud detection. Because fraud detection again is real time. So sooner you detect a fraud, it's good for the institution. So a lot of work is happening by different consulting companies on getting the use cases. Okay, how do we get the various use cases required for finance industries? Because the threat is imminent. Tomorrow, if suddenly, for example, tomorrow if somebody is going to market a computer that can break the current encryption standards, okay, so you can imagine what can happen. Immediately there are multiple countries who want to break into other countries' financial systems. They can break into other countries, defense agencies. They can break into other sensitive agencies' data. They can get in and they can crack and take the data out. Okay, so while nobody's talking about it, that's an imminent danger. Everybody's scared of. Okay. But a lot of activities also happening on that front. There are a lot of standards that are coming in the market in terms of post-quantum scenario safety standards, and there are agencies that are continuously publishing new technologies and new standards. Okay, so let's look at some of the use cases, okay, in the banking and capital markets, how we can use quantum computing. Okay, So let's look at risk management. Okay. So risk management, while we talk about risk management, it's a very common term, okay, because risks is everywhere, right? Risk can be managed in a project, in a college, in a industry. In terms of any type of risk management, what we need is a lot of data, okay, because the risk, you always see a history, okay. So there is a famous quotation, right? History always repeats. So people want to look at historical data and look at, okay, developing a model on what dangers they see in the future. So it all boils down to number of processors or amount of data the model can compute. So with the current artificial intelligence, machine learning models and the available infrastructure, we're able to see past few years of data to get a model and see where we are. Okay. So today, once quantum computing is in place, we'll be able to see much. We'll be able to see much backwards. See, for example, again we talk about COVID. Okay. So when COVID came, we all talk about the Spanish flu, okay, and those other flu and other worldwide massive disaster scenarios. Okay, imagine we had a quantum computer that had seen 100 years back data, and if it had given a view that in another 100 years we might see another disaster. But right now, with all the technologies, the next COVID or the next those mass disaster scenarios can be managed. It can be predicted with much better control and knowledge. The next is real-time risk monitoring. Okay. So while we monitor the risk, so risk can be monitored two ways. You can do it real time or do it offline. Okay. We call it online real monitoring and offline real monitoring. Consider the scenario. Consider two scenarios. Okay. A scenario where a money is being sent from person A from country one from India to person B in some other country like US. Okay. So there are different countries. For example, US has a mandated law that says that when money comes to anybody in the country, the US, or for anybody, if you have an operation in the US, you should control your financial flow. For example, when you send money outside your bank, it's the bank's responsibility to make sure the money doesn't go to shady organizations. Okay, it doesn't go to terrorist sponsors. And the US Central Bank has given a list of entities, called as OFAC. There is Office of Foreign Assets Control in the US. It gives a list of entities and the name of members to whom, if money goes to these organizations or entities, it has to be tracked. And if a bank misses this, it comes under heavy penalties. You would have seen a lot of news in agencies like Barclays, Citibank have been heavily fined by US government because they couldn't control some of the dollar transactions. MNC Bank processed a dollar transaction to an entity in Iran. Okay. And by the time they caught hold of the transaction, it was already over. Okay. So they did not do a real-time risk monitoring. So it's very important that every monitoring has to happen real time. The risk has to be seen immediately on real time so that it can be handled. Okay. So it's the scenario analysis and simulation. Again, it's the same thing that I spoke some time back. When you have different models and simulations, okay, you need to have the relevant computing power as well, so that you can have some more scenarios. For example, today, if we can process 1,000 scenarios, if we have a power to process 1 lakh scenarios or 1 million scenarios, we're going to have a better model and better simulation. So these three areas are going to enhance the risk management capabilities of various organizations. Next, we come to fraud detection. Again, it's like anomaly detection. What is an anomaly detection? So when we look at a lot of data, the systems and these fraud detection modules can look at patterns. For example, I'll give a simple example. Say somebody's credit card is lost for whatever reason, lost or somebody stole or something. There was a particular scenario it's this practical scenario. Somebody's credit card was lost and it was swiped in different banks. Okay. So the guys who stole the credit card was traveling in a train. Okay. So in every possible station where there's an ATM, they have to get down, they'll swipe, take the money, take the next train and go to the next station. Okay. So they were on the move always. So this was caught in anomaly systems, the current anomaly systems of various, there are a lot of systems at present available. Okay. So the system flagged this case saying that the credit card transactions are coming from areas that are geographically very distant, and it's physically not possible for somebody to travel the distance in this specific time to swipe. Okay, so something is wrong. There is a pattern of movement of the terminals from on all directions, okay, which is normally is getting, it's not the normal operating zone of the particular customer. So the card was immediately blocked, and the customer was told that there is some sort of risk available, present in your credit card. So this is a very simple scenario. There are multiple scenarios in terms of derivatives trading, stock trading, insider trading, on how people trade entities, trade derivatives. So if we can pick up the anomaly faster, so if you don't pick up the anomaly faster, like I said before, once the trading day is over, if somebody is going to sell all their shares today, and take the money and move out, there's no point in detecting the anomaly the next day. Okay, so this thing has to be done the same day immediately. So this is one of key application for detection. And optimization, again, whatever models that are currently present in terms of detecting fraud, those can be optimized with a lot of improvement. Okay. And it is secure transactions. This comes in the area of fraud prevention. So today, how do you make sure transaction is secure? Okay, because with a lot of cyber attacks happening, people can even mirror the sender and receiver. Somebody can talk to you as a receiver and say that, and can force you by giving a false key. They can mirror the receiver and take the money from you. You may think it's a genuine transaction, but it may not be genuine. And there are a lot of areas where in-channel hack happens. Okay, when the money moves from one medium to another medium, it's hacked in between. The communication channel is hacked, and the database will be changed. For example, there are softwares that can catch a transaction midway and change the account number, so that the beneficiary changes. It goes to some other person, some other account holder. So all those are possible. Those are possible even now. Okay, and when there are and now there are things put in place. There are cryptography encryption put in place to avoid that. Now tomorrow, with the available technology, those has to be made more robust. Any queries so far? Any questions, any doubts? Or any inputs to me? Because, like I said, we don't speak to, we don't present this through academia very often. We do this to industry. So if there is something that you want me to change in the presentation, kindly raise now.
Please continue, sir, please.
Okay. Okay, then we come to the other angles of other pillars of finance. Okay, one is asset management. When I say asset management, we are talking about investment banking companies. Okay, so these assets are not the physical assets we are talking about. We call asset management companies as companies like Morgan Stanley and other lot of asset management companies who manage funds. So you're going to invest in mutual funds. So they create assets out of mutual funds. They take money from you, buy stocks, buy mutual funds, create assets, and they give returns to you. So the important aspect here is the portfolio optimization. So what is a portfolio? The portfolio is the various stocks that you can buy. For example, let's look at a scenario. Today, if you have 100,000, 1 lakh in hand, what are the ones that are going to buy? Okay, so today there can be a portfolio where it says, okay, you put 10% in fixed deposits, 10% in gold, 20% in mutual funds, real estate 10%. So there are a lot of agencies who can give you a different portfolio. Okay, spread your money. Don't put all your eggs in one basket. Spread your money across various baskets so that your returns are optimized. This is one angle. Now, if you look at a proper asset management company as such, who manage billions of dollars of funds, so what they do, they have to invest in the various stocks where the returns are higher. And if you see, every stock and every share has a typical up and down cycle. Okay, stock price can go up and go down, and it shares a relation with the market trends. So there are specific algorithms that can detect. For example, today if bank stocks are going higher, okay, The model will tell you in another 2 months, budget is coming. When budget comes, typically construction company stocks goes down a month before and goes up a month later, or other way around, vice versa. Depends upon the market sentiments. So portfolio optimization models can exactly tell where to put the money and how do you rebalance. So this is one, putting money is one aspect. So how do you create a portfolio is one aspect. How do you move funds across the various portfolios? Okay, so today, if you see, people can sell Infosys shares and buy gold. Okay, so if we have impact of buying oil from Russia, people may want to invest in the petrochemical companies, or they may want to sell they may want to sell Nayara company shares and they want to buy Indian oil. It can go either ways. It can be both ways. These portfolio optimization requires extensive analysis and models, and quantum computing can definitely add value to that. Market prediction, again, like what I said, how do you predict a market? Okay, the trends. Financial modeling, again, the same. The models that you have for risk management, you have similar models for financial modeling as well. The risk modeling for insurance, because one thing is, risk in terms of insurance. When insurance companies underwrite a particular case, so they need to look at the actual risk that they're going to therefore foresee. They foresee in a particular risk opportunity. For example, maybe 10, 20 years back, there was a satellite that was sent by US. And one of the US, NASA was sending a satellite and it burst mid-air. And then there were 2 news on the next day. Okay, on the front page is the satellite launch has failed. The business page, there was news that the insurance company went bankrupt. Okay, because the insurance company insured the satellite. Okay, and they did not refinance and spread the risk to other agencies. So typically when an insurance company insure something of very high value, they do something called refinancing, reinsurance. So what they do, they go and spread this insurance to multiple other players as well to spread the risk with a premium. Now, those days were the days where NASA was seen as unbreakable or something that cannot fail. So this insurance company did not foresee the risk of bankruptcy, and they insured the satellite with a very high amount, and they went bankrupt. So risk modeling is done to avoid scenarios like that. Okay, so that you see the exact risk what an insurance company is facing. Okay. So a lot of models like Monte Carlo estimation. Monte Carlo model can be applied to anything, any scenarios, in any industry, different scenarios. But these days, insurance companies are more focused on having different models to see the risk that they are going to face now, 5 years down the line, and 10 years down the line. Because today, whatever may appear risk-free today may not be risk-free after 5 years. Okay, so somebody's, for example, life insurance. You're going to insure somebody for life. You're going to insure somebody for next 30, 40, 50, 60, whatever it is, whatever years it is. There are companies that give insurance, term insurance till 80 years of age. They're going to take at 21. They're looking at 60 years of coverage. So insurance risk modeling is gaining traction today, so that they see what sort of risk the agency foresee. Then you have underwriting, the same thing. How do you underwrite and price? How do you price the insurance? The pricing of the insurance is directly related to the risk that we foresee. Okay, so when you talk about underwriting and pricing precision, it talks about the same. How does the insurance company foresee the risk in any opportunity, and how does it underwrite and how does it do the pricing? And fraud detection. Insurance companies are known to lose a lot of money in frauds every year. Okay. There's always going to be false claims. There are going to be wrong claims. Okay. There are going to be a lot of fraud in terms of in the claim itself. Where the claim may be genuine, the amount and the lot of aspects of the claim may be fraud. There may be fraud in that. Okay. And so effectively, insurance companies are very prone to fraud, okay, and they're very sensitive about fraud as well. So they spend a lot of money in detecting fraud. And again, it's a pattern. It can be many times the companies understand the fraud has happened after 3-4 years after the fraud has actually happened. Okay, when they take all the historical claims, and when they do an analysis, they find out that okay, a lot of this fraud has happened, but typically they have a window in which they can go back and claim. And if the window has passed, they will not be able to get the claim back. Okay, so it again puts the importance of time. So they have to look at the claim analysis and detection within the suitable window so that they can take the relevant action. Okay, so one specific area, like I said, is Monte Carlo analysis. Okay, so many of you may be aware of this, but I just want to put it so that it gives a complete picture of why we think that quantum computing can help in terms of simulation scenarios. Okay. So while Monte Carlo analysis can be seen in many different fields, it's largely used in finance and banking and insurance agencies. Okay. Because one reason is they're used in aerospace and defense as well. Okay, but the predominant use is in finance and banking and insurance and agencies, because these industries has the money power. Okay, because they know if they fail, they're going to lose a lot of money. So they have the money muscle power to spend and invest and then see where they are going wrong and what are the various scenarios that they're going to see in the future. Okay. So why is Monte Carlo analysis a particular case study for quantum computing? So Monte Carlo analysis, by definition, okay, is a mathematical model that predicts possible outcomes of an uncertain event. Okay. So what it does is it looks at various historical data. What are our inputs, for example? For example, to a market, suppose if we have to look at various scenarios in a market, if you have a portfolio, you want to look at various scenarios of what value the portfolio can have in the market. So the inputs of those can be different inputs like a stock market index, economic indicator, inflation index, the particular company's earnings, that overall market sentiment. So there is a lot of inputs. So the system will find out how these KPIs are interrelated. Okay, so how is the stock of Infosys going to do when the market is overall down? Okay, so if if the value of gold goes down, which all stocks value goes up. Okay, so effectively, if you're going to do a cost analysis or pricing analysis, it requires a lot of inputs. So it takes a lot of input. Then it's also going to assign a probability distribution. Okay, what is the probability of this event happening? Okay, what is the distribution of these events happening? Then it has to generate a lot of samples, random samples. If the random sample can be historical, so typically like machine learning, when you have to create a lot of samples, we take historical data and slightly tweak to generate more data. So it has to create a lot of samples and run multiple simulations. Okay. Like here we say, right, the simulation can be run thousands or millions of times. Okay, because each iteration is going to make it better and it's going to build a pattern. So more simulations we run on more data, with more input, it's going to improve the quality of the output. Okay, then we analyze the results of what it gives. Okay, so this is the overall different steps in any Monte Carlo simulation. It's not related to finance. For any simulation, these are the steps. So next, okay, now this is a very simple example, this is a very favorite example of mine. When I learned Monte Carlo analysis, this is how, I initially envisioned. So I thought I'll read it on a slide as well. Okay. So when you look at 3 dice, okay, so this example talks about 3 dice and giving a value of what is the most probable output that will come by throwing 3 dice. So here, we have 3 dice becomes 3 inputs. So the initial input becomes 3 dice. This 3 dice can be in reality, can be thought of something like Sensex, inflation index, etc. And random sampling. So you create multiple samples. Okay, so you create you throw the dice multiple times, and you create different sample sets. Okay. So you can see this talks about 100 trials. You can go for 1,000,000 times as well. Then the calculation is a model. Okay. This is a very simple model of adding all the 3. So the model gives what comes out of throwing 3 dice together. Then the list creation. So this documents a value in each trial. What is the value that we got? Okay, so for all the 100 times. Then you plot. Okay. So if you look at this plot, so you will see that the most possible outcome is going to be 10 and 11 or 11 and 12. 10, 11, 12. Right? So when you throw 3 dice together, you're going to look at, most probably you're going to look at values of 10, 11, 12, 13. That's a peak. So imagine there are 100 dices. Okay. So imagine 100 dices. and you want to build with 1,000 iterations. So the value, it becomes exponentially bigger. Okay, the sample set becomes exponentially bigger. The list becomes big, and it needs more. Now the model becomes different. You're going to add a lot of times. Okay. Assume the calculation again becomes different. The calculation becomes, a square root of an exponent function of this. So the complexity increases. So while this is a very basic model, this model can become complex when we present this to industry scenarios, where the number of parameters, the environmental parameters, and the model itself can be very complex. So that's where quantum computing comes in two angles. One, it can process this very fast. For example, there is a case study where a Monte Carlo analysis, which was expected to run for multiple years. Okay. When they did a simulation in quantum technologies, they're able to get it in mere minutes. So that's the value of quantum computing in terms of Monte Carlo analysis. Okay. This is a sample investment analysis. So like I said, right, here we have those 5 factors. Okay, so what happens? What is the average return? What is the standard deviation of return? And time to retire? And there is a specific model this agency has built. And by putting all this value into this model, they were trying to understand what is the value some investor is going to get after his retirement. Okay, so here in this scenario, if you see, the model talks about 100,000 initial investment, and he's going to invest $10,000 every month, every year. Okay, and we're looking at average return of 11.2%. So year 1, year 2. So now we're going to invest this in the market. So we're going to have additional factors of how the market is going to behave. We look at the values here. In every year, the return differs. Okay, there are sometimes, it goes 38%, sometimes it goes to -0. You have different models. So when all these patterns are seen together, okay, well, if you look at year 4 alone, you panic, right? You see it's negative or 0%. Okay. Now, if you look at a holistic view of all these iterations, suppose we are going to run this 1,000 times for 1 year, and then the plot, when you plot together, you may have a better value, you have better visibility of how it happens. So this is one of a practical example of Monte Carlo analysis when you do investment. Okay, this is a very interesting case study. Okay. So there is one credit agency in a credit lending agency in Turkey called Yapı Kredi. So what they did, they wanted to use quantum technologies to estimate their financial crash. Okay, so what they wanted to do actually is they have a set of 4,000 customers. Okay, they took a sample of 4,000 customers. Okay. So if you look at their actual business, if you see the bottom part of the slide, they have almost 600,000 corporate customers. And out of these corporate customers, there are a lot of interrelated agencies. For example, if you look at Reliance, Reliance has maybe 10 or 11 group companies in getting lending money from this particular agency. There may be a lot of other groups, what we call as interrelated agencies, enterprises. We call interconnected enterprises. Okay. So what happens if one of them default? Okay. For example, if you look at the housing boom crash in the US in the early 2000s. So Lehman Brothers went bankrupt. That one entity going bankrupt impacted almost every bank in the industry. It's because if one bank goes bankrupt, okay, so this bank would have had some business with a lot of other banks. They would have given funds, they would have lent money to many other agencies, many other institutions. Many banks would have borrowed from them. So what happens if one particular agency company crash in the industry? What is the impact? So now, if, for example, I don't want to name any company here. For example, somebody like Reliance, it has 12 companies lending money, getting money from a particular bank. What if one of that companies goes bankrupt? Okay. How does it affect the other companies in the group, and how does it affect the overall ecosystem as well? If, for example, Reliance and all the customers are part of this particular bank, so one bankruptcy is going to blow the bankruptcy to all the other customers of the particular bank, and the bank is going to get bankrupt. Okay. So this is one of very prominent enterprise risk framework. They call it as financial distress among interconnected enterprises that most companies want to do. They want to do. I'm not saying they're doing. They want to do, because these models are very complex. And so people typically what they do, they take subset. You take 100 customers, 100 of your customers, and then do analysis. It takes a few months. Then you take another 100, other 200 and do the analysis. So people are able to do in the current scenario with subset of their overall sample size and try to understand what is the impact on them. Okay. Now, if you look at this particular scenario, look at the last paragraph here. So they have 600,000 corporate clients. So they took a sample of 4,000 customers and then did the analysis. Okay. So they believe that, like I said, if you do 100 customer analysis, it takes months. It takes a few months to analyze 100 customers. What is the risk of one customer on another 100 customers? Take a month, few months to solve. So they wanted to do 4,000 plus customers under the framework. So they're expecting it to do to take multiple years in classical computing. It took 7 seconds in the quantum algorithm, whatever they got. So they took the software from a company called D-Wave. So D-Wave is one of the current runners in quantum technology who are coming with quantum algorithms as of now. With limited, whatever limited infra available, they're having quantum algorithms. So they did this analysis of 4,000 customers, and they are able to finish it in seconds, 7 seconds instead of years. Now, can this be extrapolated to all other customers and for the same time for others? No. Okay, so it is more of a pilot study. It's mainly because, like you must have heard multiple times in the past 2 days, quantum computing is still in an evolution stage. It's in an evolutionary stage, and there are not practically available computers and technologies that can solve this problem once for all at present. So these are all case studies, use cases that are carefully orchestrated with the view that, okay, tomorrow if we really get a quantum computer that can be practically used with very low error occurrence, we can get into this model and start doing this. Okay, so all this, that is why it is still, if you see the approach, it is being done by R&D team. Okay, it's not done with the actual business teams. It's still under R&D. But the promise is huge. Whatever they are seeing so far is, so tomorrow, for example, if somebody is going to launch actual quantum computer, in one of the session, they said Microsoft is going to launch a quantum computer in another matter of years. Okay. So, if not decades, in years, we are going to see a quantum computer in the matter of 2 to 3 years. When such a thing happened, these industries who have already done some sort of pilot study using quantum technologies will grasp it immediately, and they will start assimilating those into their technologies. So this case study is a very important case study, and this has been projected, and this has been seen even by the World Economic Forum, and this is being seen by various other financial institutions on the impact of quantum computing that it can bring to those institutions. So these are again predictions, predictions and projections. So what are we expecting? Okay, because again, like I said at the beginning, if an industry has to adopt a technology, they have to start spending. Okay? It goes both ways. If you see industry spending on a particular technology, it means it's viable. Okay, so people are putting their money and it's going to go in a particular direction. For example, if you look at blockchains, blockchain and decentralized finance technologies, 3-4 years back, or even maybe 5 years back, like they were talking about decentralized finance or blockchains, the way we're talking today. Okay, so blockchain is the next best, cryptocurrencies, crypto tokens, blockchains, it's the next best trend in the industry. But if you look at the investment of industries in those technologies, it is coming down drastically. Okay, because people realize, when you talk blockchain, when you say it's very secure, etc., the negatives are also being seen. Okay, for example, if you look at the amount of energy a blockchain mining requires, it needs digital forms, computing forms with thousands of computers to mine a single blockchain. Because the amount of energy blockchain mining requires is pretty massive. A lot of people are coming with a lot of different algorithms to mine a blockchain, but still, the amount of energy that it needs is pretty high. And again, blockchain is also dependent on cryptography technology. So how do you mine a blockchain? I don't want to go into details on that, but again, to keep it simple, if you have to mine a blockchain, you have to solve a very complex cryptographic problem. And if you have to solve a puzzle, and you have to create a cryptographic number that is less than the published number, so that you can mine the particular blockchain. So it is directly dependent on the amount of computing power you can have at your disposal. Now imagine a quantum computer comes and it can solve it in a minute. So this technology will fail. Blockchains and other technology will fail. So I'm not saying these are going to fail. I'm saying the way industry sees these technologies is different. Okay, so now they see, okay, blockchain is also part of the current token framework, because now if you see, a lot of central banks are coming with digital currencies. You see CBDCs, central bank digital currencies, your crypto tokens, your cryptocurrencies. So technology is being adopted, but the amount of money going into these technologies, the investment in blockchain technology as it is not increasing drastically. Okay, I don't have data to present in this presentation, but it's a common industry knowledge that whatever people thought about blockchain 5 years back, it's not the same that what we are seeing today. Okay, so let's look at the projections of quantum computing funding. If you look at the amount of funding that's going to flow into these technologies, the numbers are in billions of dollars. In 2022, the overall funding across the globe was 80 million, okay. And then it grew to 2032. It's going to go to 19 billion. Okay, so every year it's going to grow at a rate of 72%. So people are putting money into this technology as of now. There's a lot of promise, and see, typically what happens in any technology, for a technology has to grow, the industry has to adopt the technology. Only then the technology will grow. If there is no takers for a technology, there are a lot of technologies, okay, and there are some technologies that are ahead of their time. For example, there was a particular startup, and 12 years back, when we were a startup 12 years back. So at the time, one AI startup came to us and then said that we have an excellent AI model, okay, and they wanted to tie up with us. Then we asked, what is that you want to tie up with us for? They said the model is brilliant, excellent model, but we don't know how to use it in finance industries. We don't know how to use it. Okay. So there was a AI startup who had an excellent model, but there are no takers for it because they're not able to tell what it's going to do. Okay. But eventually, it was taken over by another MNC giant, and they are doing well as of now. But what I'm trying to stress here is for a technology to thrive and grow, industry has to adopt the technology. And the sheer shot symptom of that, indicator of that is how much money is flowing into that. Okay, and as of now, if you see, the projections are growing, at a brilliant rate of 72% per year, and it's going to hit 19 billion in 2032. Okay. Now, this is on the investment side. Okay. So, using this investment and technologies, how much value is the financial industry is going to see? So look at these case studies here. Okay, the different areas of finance, for example, corporate banking, Western cyber security, retail banking, payments, asset, investment banking, whatever it is, whatever we have seen so far. They're talking about creating so much billions of value based on the investment. For example, they say by 2035, corporate banking would have added value of 190 billion US dollars. Risk would be $160 billion. Okay. So you can see this hand in hand. There is money flowing in, and there are also agencies who project that they will make more value out of quantum computing. For example, if you look at again the numbers here, the financial industry is going to spend only 19 billion in 2032. Okay. By 2035, they're looking at a saving of 622 billion. We're talking about 20-30 times of the number. So all the indications are there for the industry to adopt. So the path is set already. If you look at it, one important thing here, if you look at this particular graph of the amount, okay, investment amounts, there are dark and white areas of the tall charts. If you look at the dark area, it says on offensive capabilities and defensive capabilities. This is what I said at the beginning. Okay, quantum computing can present you with both scenarios, offensive as well as defensive. Okay. So offensive is when you start using quantum computing to make your life better, okay, to make things happen, to show positive disruption to the industry. The defensive capabilities on the other side is on the cryptographic side. Okay. You also have to spend to defend yourself. Okay, so you expect somebody is going to come with some technology and that's going to break your system. So if you look at the breakup of this spending, again, if you look at year 2032, the last tabular tall chart. If you look at that, $15 billion, okay, is going to go in offensive capabilities. And almost $3.7 billion is going to go for defensive capabilities. So quantum computing is going to create a cost as well for every industry. They also have to invest in protecting themselves. Okay. Well, let's look at what are these offensive and defensive capabilities. Okay. So the offensive applications. If you look at how we are going to attack, how we are going to attack an existing infrastructure. Okay. Like you said, you can actually break encryption. Encryption can be broken easily. And even suppose today, what happens? If you have a offensive application, for example, today a bank does a penetrative testing, it does a security testing on audit, and it's going to plug the loopholes. Okay. It takes maybe another month or two for hackers to break it again. Okay, that's why there is a specific frequency set for security testing. So now, if you're able to break it, so imagine a computer is there, if it's going to break it the same day. Okay, so you develop a technology, or you develop a methodology, you plug the loophole, and somebody's going to break it the same day. So that's another risk that the industries face. So faster attack development is that, so you try to plug a loophole, you try to protect yourself, somebody's going to break it again, and they're going to have more attacks. The last one is that harvest now, decrypt later. This is what I was talking about, harvest now, decrypt later. When you take the data today, okay, you collect encrypting data today, and you can decrypt it later using quantum computer in the future. Okay. So today, if you look at, these are all again, you will see a lot of news articles in the news media about the interaction of China and US on quantum computing. Okay, so there's always a doubt. There are always allegations by one country and another. China always blames. Okay, it's possible US takes data from China. US says China may be taking data from US. They're all allegations. May not be true. Maybe true. We don't know. But the fear is there. Okay, people fear that today, if you can get encrypted data with which you can not do anything today, it can still be broken tomorrow with latest technologies. So that is something that we are very careful about. Okay. So defensive application is how you protect yourself. So you create cryptography, quantum resistant cryptography. Okay. So you do enhanced detection and response, secure communications. So these are again what we discussed some time back. The application is to defend yourself. You create technologies that are resistant to quantum attacks. You start detecting the anomalies and attacks faster. Because sometimes what happens, there are incidents where somebody would have hacked the system and it takes 3 days for them to find out. Okay. So even detection of cyber attacks is critical. And secure communications. How do you share secure communication? For example, if you have to transfer a key, okay, a private or public key, how do you communicate securely? So that even if the key is received by somebody, they don't be able to break it. And if they break a key, you should be able to find out that the key is broken. Okay, so this is the current cryptography scenario, right? So currently, if you look at cryptography, we will look at two algorithms, symmetric and asymmetric. So you either encrypt something through a public key, and you have a symmetric key with both, or you have a public and private key. You encrypt with the public, and somebody is going to decrypt with the private key. Okay. So this is the current scenario today. You have players like RSA. These are big industries, RSA, DSS, okay, who use this cryptography and encryption technologies. This is at present. Okay, what happens tomorrow? Okay, so tomorrow we're talking about some technology called quantum key distribution. Okay. So how does it actually work? Okay. So when you encrypt a key and send, as of today, it's no more valid in the future. In the future, we are looking at a scenario where no encryption is secure. Anything encrypted with today's technology can be decrypted tomorrow. Okay. So we are looking at a scenario where the conventional encryption algorithms will not be used in the future. In the future, we are going to look at different types of encryption and different type of communication of the keys. Okay. How do you securely communicate a key to the other party? Okay. So one of the promising area technology that is being proposed is a quantum key distribution. Okay. So talking about instead of a private or public key, we talk about a quantum key here. We look at, so this, they say this is using the principles of physics, right? The optics, photons, they use photons and optical interface to move data from here to there. So the idea here is using QKD, you become immune to attacks that can decrypt your encrypted keys, because the key itself becomes different. It's no more the encrypted the text or file. It becomes a set of photons that are going to go in an optical fiber. So this is how it works. Okay, in the current technology, the first step is quantum transmission. So what happens is, instead of having a key, because today if you look at a key, is a set of random, text. Okay, the hexadecimal, whatever text it is random text as of now. A tomorrow's key may not be actually text based. It may be different waves of light, photon. Okay, so in this case, in quantum key, what they do is, the current scenario is, so party A sends set of photons to party B. Okay, the standard Alice and Bob scenarios here. So Alice send individual photons through optical fiber to Bob. Okay, over a channel. So the channel here is, because we're talking about photons, the channel here will be fiber optic cable. Okay, so one person is going to send a set of photons on a fiber optic cable to another person. So how do you encode these photons? Because photons are mere light particles, right? How do you encode it? How do you encrypt this? So since these are photons, the current technology uses a polarizer. Okay, so you use a polarizer and polarize different photons differently and send it to the other side. And when the photon actually moves, so these are quantum states. Okay, so the polarizer is going to send it in a quantum state. It's a no more bytes, no more bits, 0 or 1. Okay, so you're going to have multiple states of different polarization of the photons that goes to the other side. And when the next party receives the photon, okay, they'll have another key to intercept, okay, and look at the polarized level. Okay, so how does it, so they'll have previous understanding of what sort of polarization they're going to send from here to there. Okay. So the receiver is going to apply the same polarization principle and read the photons, and then see if the photons align with the polarization expectation on the receiver side. Okay. With of course with some sort of error threshold. So when they see these photons and the polarization within acceptable limits, they will know that the key is secure. Okay, its encryption is correctly decrypted, and the key is secure. Because here, like in quantum mechanics, when you say about Heisenberg principle, if you measure something, the state won't be the same. Okay, the state changes with every measurement. So today, if someone is going to look at the photon, because optical fiber is again a common public mechanism, somebody is going to tap into the optical fiber and look at the various polarization states. The moment they measure the photons polarization, the state is going to change. So when the receiver receives the photons and when they do a depolarization, they will understand that this has been broken somewhere in between. Somebody has actually eavesdropped and measured it in between. So it's sort of secure, and it's also easily detectable. Okay, so how do you detect that if somebody has encrypted in between, decrypted in between? So the advantages are like this. Okay. So no more encryption algorithms. So no fear of saving algorithm somewhere. Tomorrow, if you lose an encryption algorithm, nothing is going to happen. There's no algorithm here as such. And the detection of eavesdropping. So today, if the photon moves on optical fiber, and if it is met in between, if somebody is measuring in between, it will be seen with the other party. And since they don't, this technology does not depend on standard bits of zeros and ones. So these are looking at multiple states of quantum computers. So even in a scenario of quantum computing, post-quantum scenario also, nobody will be able to break it with just massive computing power. The other way is, if you're going to have a massive computing power, you can break any encryption. But this sort of quantum photon polarization cannot be decrypted easily. Now challenges. Well, okay. Now all of these quantum technologies also come with the current challenges. These are challenges as of today. Okay, so the focus is in another 10 years or so. By the time when you are in 2035, people expect, the industry and academia expect most of the challenges to be sorted out. Okay. Now let's look at today's challenge of quantum key distribution. Because it's an optical fiber, Okay, the limit of is on the distance part. Okay. So we will not be able to use this beyond 200 kilometers. So that's where the optical fiber loses its transmission capabilities. So if you have to extend it to further distance, you would have a repeater, and the repeater again is still in research stage. So as of today, even if you are going to bring in a quantum key distribution technology with any institution, the max it can cover is 100 to 200 kilometers. It can't go beyond that. And again, the current polarization technology, we need to. It's going to take some time to polarize the photons and create a key. As of today, encryption, the current encryption technologies have come a long way, so the encryption happens very faster. But this is a radically different type of encryption. It's going to take some time. Okay, so at present, the key generation rate is pretty low. It's pretty slow. And again, the cost and complexity. If you have to generate photon, if you have to polarize the photon and send it over an optical fiber cable, and somebody has to receive on the other side, read the polarized state of the photon. These are going to require massive infrastructure investments. People are going to have expensive hardware, and even with maintenance. Tomorrow, somebody is going to cut the optical cable somewhere in between. The whole principle is lost. Okay, so the optical fiber has to be protected properly through expensive technologies and sheathing and covering, etc. So the complexity is still there. Okay. So, like I said, in the coming 20 years or so, 10 years is what the people forecast. In 10 years or so, a lot of these challenges must have been sorted out, and we should be able to use these technologies in some form or other. Maybe tomorrow it may not be like maybe radio waves. We don't know. But this is a principle that's present as such. Industry foresee in another 10 to 15 years, this will be available off the shelf for somebody to adopt and use. Okay, so these are the projections. Okay, if you look at the cyber attacks, okay, so this we are talking about at risk before 2025 and between 2025 and 30 and beyond 2030. So if you look at risk before 2025, okay, you have insurance, public sector, and banking, so key areas. So these are the ones that are at the risk as of today, okay, before 2025. But the system, what the industry foresees is after 2030. Okay, the way the industry is evolving as of now, especially the insurance, the banking sectors, they have proper systems in place to ensure that the cyber attacks are minimal, or they are not the sole target of cyber attacks. Okay, so what is crypto agility? Okay. So when we're talking about institutions moving from current encryption technology to future encryption technology, so these are, while it's very easy to put it in a slide and talk about, right? It's very easy to say, okay, a bank has to move from current encryption standards to post crypto encryption standard. But not every infrastructure will be agile. Okay, not every system and architecture will be agile for us to get in new technologies. So what is that needed to do for companies to move to crypto agile systems? So what it actually requires. So today, suppose a bank is moving from current encryption technology to post PQC, post crypto encryption technologies, post quantum encryption, cryptography. So what happens? You have to take all the data that you have as of now and re-encrypt the same and keep and protect it again. Okay. So at any point in time, you may have data on both sides. You may not want to encrypt every data you have. You may have a hybrid approach where some of your data, old data, may be in current encrypted stage and some may be in advanced stages. So crypto agility just shows every institution has to be agile, okay, on this angle, so that their architecture, their systems, their overall infrastructure remains flexible, so that they can adopt quantum technologies in the future to meet their needs. Okay, so this is talking about post-quantum cryptography. PQC, you will see this term called PQC everywhere. So I just wanted to cover that as well here. So PQC, what we are looking at as of now, are not based upon factors. So today, the traditional cryptography based upon factors, large factors. You have a prime number, and even a supercomputer will be difficult for you to find those two important factors. It takes a lot of time. So in the PQC scenario, those are not going to be on factors like example like the mathematical problem. They may have mathematical structures like hash functions, etc. So, and examples, as of now, you have this typical RSA, ECC, Diffie-Hellman, those give standard encryption technologies as of now. Tomorrow is going to be different. They're going to have lattice-based, code-based. You don't have a lot of players in this area as of now. It's still an evolving area, but they're going to follow this sort of latest technologies and approaches to have PQC in place. This is another interesting case study, okay, on what HSBC did. HSBC has a platform, it has a digital asset platform called Orion. Okay. So what it does, it tokens gold, it tokenizes gold. Okay. So you can actually invest in gold in HSBC. They sell gold as tokens, and the token is stored in a system called Orion. They have a digital assets platform. So this is based on DLT, distributed ledger technology, which is other name for blockchain is an example of DLT technology, right? So this is based upon DLT technologies. But like I said before, a DLT technology is heavily dependent on encryption and cryptography. If somebody can break encryption and cryptography, the DLT system fails. You will be able to hack the DLT technology immediately. The moment you can hack encryption and cryptography. So since they have built the entire digital assets platform in DLT, so HSBC foresee the risk. They could foresee the risk of what will happen in the quantum era. What will happen? Because tomorrow somebody can just wipe out all the gold in a second. The moment they break this DLT, they'll take every gold out, and there'll be no trace of that also because the DLT itself would have broken. DLT people adopt because it has a track of all the events and activities. But in a scenario like this, where the DLT itself is hacked, even the traces won't be there. So HSBC did a case study of that. They started using PQC VPN, a quantum random number generation. So they were trying to put a lot of whatever technology is available as of now. And to some extent, they have protected their digital assets platform today, as of today. So at present, this is one of very important case study of post-quantum security scenarios. A lot of banks are looking at this case study and how do they improve their security scenario as of now. But like I said, this is at present. These technologies continue to evolve. Tomorrow you may have a different PQC standard and they have to adapt to that. It is still in a very fluid state. We hope in another 10 years, we'll have systems in place that will work against all sort of quantum threats and cyber attacks. So what are the challenges in the adoption of quantum computing? So today, if you bring quantum computing system, how is it going to merge with the existing classical systems? Because today, every company, every institution today is working on classical computers. Now, when you bring in quantum computers, there has to be a strategy on how do you bring a hybrid model of where a classical computer also talks to a quantum computer. You cannot have two systems that doesn't talk to each other. It's very difficult to have an environment like that. So how people are going to adopt will depend upon how fluid and how flexible the architecture is, whereby they can bring in a quantum computing setup and make it speak to the existing classical computing setup. And the hardware limitations, like this, you must have heard it a lot of times in the last 2 days. It's again, a lot of quantum technology is still on a pilot stage. A lot of hardware limitations like the temperature at which you have to keep the qubits, the cryogenic temperatures, and the stability of the qubit as such. But tomorrow, if there are going to be some sort of disruption in terms of temperature, interference, whatever it is, if the qubit is not stable, so it's going to impact the overall system as well. So this is another area of hardware limitation. The third one is on the skill set and expertise. Like even if you look at present, the skill set talent pool and skill set pool on quantum computing is pretty less. Okay, it's still an R&D stage. A lot of investment you see in companies like IBM, Accenture, Microsoft, Google, Amazon. If we look at the Google and Google Cloud and Amazon Web Services, you also have these quantum algorithms available in their cloud. So if you actually go to AWS Cloud and Google Cloud, you can get a hold of some of the quantum algorithms. While that is happening at a very high level, the actual number of talent, the actual amount of engineers and researchers who do work in this area is still limited. We don't have a lot of people. And tomorrow, if this comes to the market, we also need a lot of engineers who has to work on these technologies. So this is something that is people have to act as of today. The academia and the industry has to look at these aspects today so that they can start building the talent pool for tomorrow's environment. So one of the other areas is payments. So I want to bring this payment angle here, although it's a very small subset of banking business. I want to bring it here because the amount of money it handles every day. Today, if you look at most of our Indian population, we use GPay, right? GPay or UPI. We start using these wallets and UPI interfaces. So the world is moving towards enhanced payments. So there are standards like SWIFT, where foreign currency moves from countries to countries. There are people who have come with technologies like Ripple tokens. Instead of sending SWIFT money, they send through Ripple tokens. So a lot of technologies. It's a very thriving and evolving industry. Okay, where a lot of technologies keep coming to make payments simple. If you look at the scale of payment industry, if you look at Visa, Visa is just one payment provider. What Visa has done, it processes almost 613 million transactions every day. Okay, and in 2024, they processed total of 234 billion transactions. Now imagine the scale of this. In these transactions, even if they were able to make 1 cent per transaction, look at the amount of money that they made with 234 billion transactions. And the volume, the payments volume Visa handled in last year is $13.2 trillion. So, and this is a fee that Visa is going to make. They collect this sort of transactions, this interchange fees from every transaction. So, payment. What are the unique features of payments? Massive data processing. Payments are data intensive. Okay? When you send a payment instruction from one person to another person, the data is going to have details of the sender, the receiver, the amount, the date, the charges, the commission, and where it has to go. Because if you send, for example, you're sending money from here to State Bank of in New York branch, the money will not go directly from your SBI here to SBI New York. It has to go via currency correspondent. It will first go to Citibank US, and from there it has to go to the SBI New York branch. So money has a path of moving. It cannot move directly from one bank to another bank, because these banks will have accounting relationships among each other. So the money will move from one bank to another correspondent banks. This is a unique feature of payment industry. When money moves, it moves across multiple correspondents, and each correspondent is going to have some sort of commission or charges. Okay? So they take some sort of commission at every level, and the money moves further. And customer loyalty. There are a lot of payment providers in the market as of now. If you look at GPay, for example, I don't know how many of you use GPay. It's pretty common now. In initial days of GPay, every transaction you make will have a reward. Okay? The moment you make a transaction, a reward will come saying that you got a reward. You want to use it today or tomorrow. Now there is no more there. Okay? So that is a tactic they use to enter the market. But again, now today there are a lot of players equivalent to GPay. You have Apple Pay. You can pay through WhatsApp. You have multiple providers. Right? You have Evolute, but separate tokens by which you can make a payment. So what keeps customer glued to separate a particular payment provider? So payment industry has to keep thinking about how do we keep, what sort of loyalty programs they have to use, and they have to keep customers with themselves. And fraud detection. Like I said, payments are very prone to frauds because money moves from one entity to another entity with multiple entities. It can be hacked at any point in time. Details changed, value changed, account number changed. It can happen anywhere. Okay, so they have to invest a lot of money in fraud detection. And encryption. This is a very classic case of encryption. The payment is encrypted on both ways, when it leaves a node and it enters a node. Okay, and in transit also. So data is encrypted at rest and at transit as well. And payment industry is an area where it gets encrypted multiple times at every node, again and again. So how quantum computing can help payments processing? Like I've shown here, when you make a payment, when you swipe your card and when you make a payment of the particular merchant, it goes to a payment gateway, which does a fraud resolution. and it goes to the merchant's bank, and then it goes to a payment processor, and it goes to the card scheme. It checks whether it is a Visa or a MasterCard or a Beam or UPI payments, and it goes to the actual bank, the cardholder of the bank of the cardholder. Okay, this is a very standard, simple, basic scenario where money moves in this angle. For example, suppose you are going to bring international card. Okay, you're bringing a card from UK. For example, Revolut use cards in UK. Okay, you're bringing a card from UK and you're going to swipe in India here. So the number of participants of this in this flow increases drastically, because your card provider in your country will have a relationship with some other card provider, service provider in India. So we have to find the route of the payment. Money, how should the money move from the particular card holding bank to the merchant? Okay. So this is very important in Indian-based scenario today, because India, if you look at the last 3-4 years, our UPI has gone places today. Today, if you look at the UPI volumes, massive UPI volumes happening every day. And UPI is being accepted by multiple countries, even outside India, right? Many other foreign countries are adopting. Now, even UAE says they will adopt UPI. Okay. UPI as a technology is being adopted across multiple countries. So this is something that, can make UPI better. And UPI, if you look at the technology as such, currency is what the economic control is. Today, we are having something like BRICS. The agencies like BRICS, where we are talking about a common currency against USD. So there's always a fear, right, that tomorrow if an agency like SWIFT is shut down, they may not have the banks, the other countries may not have enough avenue to move their currencies. Okay, so having an alternative network, having a parallel payment processing system is going to help every country to protect their sovereignty and independence. Okay, so they can have their own economic policies. They won't be at the mercy of other banks. So technically today, if few countries who control SWIFT network block India out of the network, we will not be able to do any business and payment transactions. That's a reality today. So these investments in payment technologies will help India stand independent. So a lot of investment is going in this area. We'll have to see how it evolves in the coming years. So these are some of the case studies, okay, on what has happened in payments processing. We're coming to near the end of the presentation. There are just a few more slides left here. So improved fraud detection. Bank of America explored QKD. Like I said, they just explored here. Okay? They do not have an existing system that helps them to protect the data as of now. So they have tied up with another agency to have a QKD distribution to protect their cross-country transactions. They will be called as cross-border transactions. Then the enhanced transaction security and speed. If you look at the Bank of France and Deutsche Bank, the German bank and the French bank wanted to see the performance of messages. Okay, today, if you look at cross-border transactions, they're going to have if you have to send a fund from India to US, for example, today, it may take a day or two for the money to reach, okay, between two banks, not from sender to receiver. Between two banks, it may take a day or two. If you're going to send a bank money to somewhere in Africa, it may take 3-4 days for the money to reach. That's a reality today. So a lot of banks are investing because, see, if you look at the 4-day delay, one of the bank is going to lose the interest income. They're going to send $4 million today to some other bank, and 4 days it's going to be in transit. Okay. It's neither in your account or not in their account. So both the sender bank and the receiving bank are going to lose in terms of interest. So different banks are trying different methods to understand how do we fast track this? Okay. How do you increase the performance of this? And QRNG, okay, there is case of Samsung. So Samsung is toying with the QRNG generator in their high-end smartphones, so that like I said, the real random number generators for security and other making payments. Samsung is already there. They kept one leg there in their smartphones. Okay, so this is an important question. How soon do we need to worry? Because in my presentation there are also negative situations, negative scenarios where we said we have to protect ourselves. There is a scientist called Mosca who comes with a theorem. So he says it's pretty straightforward. It's just common sense, but still, this has to be part of every security thought. Okay. So how much time it's going to take? How much time data must remain secure? For example, if your data it needs to be secure for 10 years, after 10 years, the data may lose its value, right? Today, you may have a formula of medicine. 10 years, you may think that, advanced formula may come. The data has to be secure for 10 years. And how much time that your agency needs to upgrade to cryptographic standards. Okay. And at what time? And what is the time frame for the industry to come with quantum computers that can break cryptographies? So it says if X plus Y is greater than Z. For example, the number of years you need your data to be secure and the time you're going to take to make it secure is lesser than the time somebody is going to bring a quantum computer into the market, you have to panic now. You can start worrying and you have to start working on that. So, so there are security agencies who keep looking at the industry, at the market on the developments. So if somebody, Microsoft says, I'm going to launch a practical quantum chip and a practical quantum computer in another six years, or say 2 years, 3 years, whatever it is. Every bank has to understand that they just have 1.5 years left, or 2 to 3 years left to secure the data. So this Mosca theorem is in every security detail, where they have to look at the current readiness and make them more agile and ready for future technologies, and also look at the market trends. This is the path to post-quantum cryptography. What is the path that you're going to take? You have to look at the current encryption method and not wait till the entire cryptographic algorithms comes. You can have hybrid cryptography. You can look at the current traditional encryption as well as post-quantum encryption. And there are a lot of standards, this NCSC standard. NCSC is an institution that gives regular updates on quantum developments and quantum standards. So this institution has to stay abreast of in the NCSC standards. And cyber security is an upcoming field now. As of now, if you see, even if you look at the number of courses available in the industry, in the market today, in the various institutions, India and abroad, cyber security plays a very major important role. And the number of courses are also very high. Okay. So it's going to be a very important career option in the current 10 years or so. So we have to look at these institutions have to engage with cyber security experts so that they do a thorough audit and look at the readiness. So this we discussed before. Okay. So these are my references that I have taken. Okay, so I will share the PPT with the coordinators team. You can look at this article. These are very important articles by major consulting companies who are given a very interesting view of what quantum computing can do to financial services industry and where we are heading to. Okay. So I'll request you to go through these links and get more insights on how quantum computing can affect the financial services industry. So this is where we are, and we have come to the end of the presentation. If there are any queries now, I think we have 3 minutes left. I didn't have any questions so far. So if you have any queries to ask, kindly do it now, or even you can connect with me offline and ask your queries later.
Yes, sir. It was a great presentation. Thank you, sir. Can I ask a question?
Yeah, sure.
Yes, sir. Yes, sir. And as an educationist, so what are the technical skills we need to acquire in quantum computers, sir?
Okay, so from a technical skills, if you look at, like I said, right, in the cloud, for example, Google Cloud, AWS, okay, every cloud has a different set of quantum algorithms available as of now. Okay. Today, the technology is still in the research R&D stage. Okay, you will see the quantum labs of IBM. Like there are a lot of speakers from IBM quantum lab as of today. The industry is still in the industry stage. It's not moving to the production stage. Okay. But for now, it's important for educationists to look at the trends. For example, like I said, cryptography, right? To look at the trend of how quantum computing can impact an industry and adapt to those technologies. The technology as such is very nascent. It's not there in the open market for others to adopt and learn as of now.
Okay, sir. Okay. And you said the quantum bits are transmitted. So I got an idea how it gets transmitted, but how it gets stored, sir, actually. See, normally we store data in HDD or solid state devices, but quantum data, how it is getting stored?
Quantum is not for data storage, it's more for data processing. Okay. The area what I talk about is the communication of a key. Okay. Say, for example, so today, the same example, let's take the same example what I told. You send a set of photons today. Okay. You send a set of photons, At the polarizer level, you will know the polarization you did for every photon. Okay, the system will tell you this is a level of polarization at every photon. That's your data. That's your key. Okay, the recording of the polarization is the key. And at the receiving end, somebody should be able to decrypt and depolarize. Right? And when they depolarize, also they're going to read the polarization state. So quantum data is a state of the particular qubit or whatever we're going to call about. Quantum is in terms of state. It's not going to have so data at any point in time.
Oh, okay. Okay, sir. Thank you. Thank you, sir.
Thanks.
Mr. Venkatesan, really excellent presentation. And this presentation actually forms a complete document, a valuable document for the people of the finance industry. How these quantum computers are going to have its impact in the finance industry. And your explanation on Monte Carlo simulation was really enlightening. There is a thing, many of our participants may have the doubt that the Q signals degrade over long distances. Because in the previous lectures, they have been listening to the quantum entanglement, which is capable of connecting some light years. So this question will be there. Then we will discuss about that later. Thank you very much, Venkatesh. On behalf of all the participants, I thank you very much. Really an excellent presentation. Thank you.
Thank you, sir. And again, I want to thank you for the opportunity. Okay, so this is a very interesting opportunity for me to present. Like I said, right, I'm more used to hearing from academia. A chance for me to present this to the academia as well. Thank you again for the opportunity.
Thank you. So now we are having a great person with us, Dr. Venkata Subramaniam, who is really doing wonderful things in the quantum computing, especially in Indian arena. Right now, many of us could see his achievements in his LinkedIn. So it is great to have you, sir, with us. The title of the FDP now it is going to be taken by Dr. Venkata Subramaniam. Thank you, sir. You will have a brief introduction about Dr. Venkata Subramaniam. Right. Please, sir.
Thank you so much. Good evening.
It's my pleasure to introduce Dr. L. Venkata Subramanian, IBM Quantum India lead and IBM master inventor, based in New Delhi, India. With an impressive long industry experience, Dr. Subramanian has led several pioneering initiatives in IBM related to quantum computing, cognitive technologies, and large-scale systems design. As an IBM master inventor, he has contributed numerous patents and has been recognized internationally for his research and technical leadership. His lecture today on quantum computers and AI, a potentially transformative synergy for future of India, will help all of us understand the broader vision of integrating these cutting-edge technologies for national growth and innovation. Thank you, sir.
Thank you so much, sir. Are you able to hear me?
Yes, sir.
Yes, sir.
Okay. Thank you. I'm just going to start sharing my screen. Okay, just give me a minute, please. Okay, I think I have to log off and log on. Can I do that, please? It's not allowing me to share. I'll just come back. Just give me a minute. Yeah, hi, I'm back. I'm going to start sharing. Okay, good evening, everyone. So I'm going to today give you a glimpse of where is quantum computing and where are we headed. And I'll also talk about where is India's opportunity in this. So in the next 1 hour plus, my goal is going to be to take you through this journey. And also, please feel free to ask any questions that you have, because what I want is for you to, at the end of this talk, exactly understand how you are going to contribute to India's quantum mission. Okay, that's the goal of this talk. Okay, to make sure each one of you understands how you can contribute to India's quantum leap, how this decade we are going to turn it into India's decade, and how we will make quantum a tool for our development. Okay, so, and in that tool, how are you going to use it is the big question. Okay, so to begin with, we all use programming languages like C, C++, Java, Python. These are called higher level languages. In these languages, it is mostly English-like syntax is used for loops, while loop, all sorts of pseudo English language is used to write these programs. Okay, so whether you want to do AI, you want to do some sorting, you want to do some optimization, anything that you want to do, you are going to write code in one of these higher level languages, like Python. Then what happens? This Python code is then compiled, and the compiler does what with it? Please feel free to write in the chat window. Okay. Feel free to write answers to questions that I ask you. So what does the compiler do to this higher level language that you write your programs in? That gets converted into machine code. The machine code is what runs on that processor. So whether it is your mobile phone, whether it is your laptop, your desktop, or any supercomputer, the higher level language code that you write gets converted into machine code, and that machine code is in what language? So the primary unit of information on your laptop, on your mobile phone, on the supercomputer is zeros and ones. So what happens is your higher level language code gets converted into a string of zeros and ones, which then runs on your classical computer, which can be a mobile phone, which can be a laptop. So I hope people can hear me, because I can't see anything. I can only see my slides here. I don't see anything coming on the chat window, and I can't hear anyone. So I hope you're able to hear me. And we are still connected. Yes, sir. Okay, very good. Okay, So now, so your classical computer, you write in higher level language, that gets converted into machine code, which runs on your laptop, mobile phone. What happens on a quantum computer? What is different? You can chat, type on the chat window. Does the higher level language change? No, it is still Python. So on a quantum computer, you write code using the same higher level languages like Python. Then what happens to that Python code? So the compiler or the transpiler on the quantum system converts this higher level language into machine code. In this case, what is the machine code? Is it zeros and ones? No, it's not zeros and ones. And that's where the difference comes. So the higher level language which you use to write your programs is still Python. A Python library called Qiskit is the most popular programming language for quantum computers today. Qiskit is a Python library. So same higher level language, but this code on your classical computer gets converted into a string of zeros and ones. But on your quantum computer, this gets converted into a string of qubit operations. Okay, bits, zeros and ones, qubits. I'm sure you know what qubits are because you've been going through some earlier classes. So we'll come to that. So now this is the Summit supercomputer. This used to be the most powerful supercomputer in the world. Now it's at number 8, 9, 10. I'm not sure which number it is. So you all know Moore's law. What is Moore's law? Moore's law states that every 18 months, compute power doubles. 2 times, 2x. Compute power doubles every 18 months to 2 years. And that's why almost every year, every 2 years, you go and buy a new mobile phone, a new laptop. Why? Because they have more powerful camera, much faster processor, much, more bigger games, bigger AI programs you can write. So all of these, the supercomputer has been doing several things for us, of course. We all use mobile phones today. We all use laptops. So there are several things which we can do using our computers, which are very powerful, as you know. But are there things that your computer cannot do? So one example of what a computer cannot do. If you wanted to simulate a molecule of caffeine, caffeine is something you find in coffee, for example. If you wanted to simulate a single caffeine molecule for a single fraction of an instant, a fraction of a second, if you were to do that on the best supercomputer, you would require 10 to the power 48 bits to represent the energy configuration of a single caffeine molecule at a single instant on a classical computer. And this is 10 to the power 48 is actually 1/10 the total number of atoms present on Earth. Are we ever going to build a supercomputer that big? I don't think so. And that's where a quantum computer comes in. A quantum computer only requires 160 logical qubits to do this. 160 qubits versus 10 to the power 48 bits. 10 to the power 48 bits to represent a single instant of a single caffeine molecule versus 160 qubits. So that's the difference. Okay, so I just gave you one example of a problem which can be solved on a quantum computer, but which cannot be done on a classical computer. Are there other problems like that? So there is one more problem called prime factorization. What is prime factorization? What are the prime factors of 15? 3 into 5. What are the prime factors of 49? 7 into 7. What are the prime factors of a very large integer? 3, 9, 8, 2, 6, 5, 1, 7, 8, 2, 9, 7. A 2048-bit integer. It would take 8 billion, billion with a B, billion years on the best supercomputer. 8 billion years to factorize a 2048-bit integer. And so prime factorization is what we use for all our encryption today. Your passwords, your banking transaction, this Google Meet call, if somebody were to catch all the signals standing outside, they caught all the signals, will they be able to listen to us on this channel? No, not unless they log in. Without logging in, this conversation is encrypted. Your WhatsApp chats, all of them are encrypted using this very simple fact called prime factorization. Because it cannot be large numbers cannot be prime factored, so they form the keys for our encryption today. But in 1994 showed that all it requires is 8 hours on a quantum computer. Theoretically, he showed 8 billion years, 8 hours. Exponential speed up on a task like prime factorization. Of course, after Shor's algorithm, we have been looking for quantum safe encryption techniques, and recently NIST came out with quantum safe standards, and the whole world is now moving from prime factorization based RSA encryption to quantum safe encryption. Okay. A third problem, learning. What is AI? Does anybody know what is AI? AI is about teaching your system using examples, teaching it about anything in this environment. Okay. So for example, cat. And intelligence is something we humans also possess, right? So as a child, how many cats did you have to see before you started recognizing cats? Maybe 1, maybe 2. For a AI system, how many cats? Does anybody know? How many cats do you require to train your AI system to recognize cats? The same cat, you require 1 or 2 examples. As a child, you needed that before you said, Mama, cat, Papa, cat. All you needed were 2 examples, 1 example maybe. And then a cat comes in front of you and you say, cat. But for an AI system today, it requires thousands of cats.
Yeah, the more the better for AI.
Yeah, you need cat from this angle, cat from this angle, occluded cat, all sorts of cats. And so what is happening? Every time an LLM or an AI system comes up, what happens on the other side? A power station has to come up. Because you can eat rice and dal and stuff and recognize cats, but AI system, because of the inefficient representation and inferencing that it does, it requires thousands of examples, lot of complexity, so it eats lot of power. For you, that power is 1 roti, 3 rotis maybe, or some dal and some sabzi. For an AI system to do the same thing, it requires lots and lots of energy. So what is happening? Every time AI systems come up, power stations come up, and today many of the tech companies are actually buying nuclear power stations to run their AI systems. The current US president, the first thing he did was on January 20th, declared an energy emergency in the US. Said, to run our AI systems, to lead in AI, we need lots and lots of power. So I declare an emergency in the US for energy. And that's another problem which your quantum is likely to come in and solve. 1 cat, 10,000 cats for current AI, classical AI. Quantum brings it closer to the human processor. Maybe not 1 cat, a few tens, but there is an order of reduction that many people are observing in quantum systems. So I gave you 3 problems now. First one was molecular simulation. Something like a small molecule of caffeine. It's so hard to simulate. But for a quantum computer, we expect this to be much easier. Second problem was prime factorization, a maths problem. Third problem was learning, AI. So I'm going to give you a break here for asking questions. I think
Why
we
the
can-
caffeine molecule is so complex, sir?
Sorry?
Why the molecule of a caffeine is so complex?
Caffeine is not at all complex. It is one of the simple molecules. The problem is because using binary digits, zeros and ones, you cannot simulate nature. That's the problem. Just like cat is not complex, you and I get cat very easily. Cat, dog, hand, all of these. But it is because we are using this zeros and ones to represent nature, to represent molecular phenomena, which is more complex than zeros and ones. That is the reason why using something, a computer which is based on zeros and ones, it's very hard to
So-
represent.
So the
Yes.
qubit will do more than a binary.
Yes, so we'll come to that. Yes, exactly. That's a very good point that you've made, that this, it's The complexity is not in the data. Nature is doing it. Caffeine is there and it's a simple molecule. On your body, the proteins are much, much more complex, bigger molecules. They are also all working, you know. Problem is because in our classical computers or your today's laptop, mobile phone, supercomputer, you are representing everything with the fundamental unit of information, zeros and ones. And that's the challenge. Okay. Any other questions before we go back? Okay. So I'll ask you some more questions now. Please raise your whatever, you know. I think you can do these sort of things here. I don't know if you can. Are you allowed? Or are you allowed to chat? So which country do you think has the maximum quantum trained people? Those who think it's China. Those who think it's US. Those who think it's India. Okay, so keep that question also in your mind. Okay, so there are questions which I will keep asking you from time to time. Okay. Okay, so we'll go back. And if you can, please enable question answering. That is very good. If people can ask questions and at least on the chat window, that will be nice. So the limit of the bits, as Sir asked this question, you know, why are we not able to simulate a small molecule of nature, caffeine? It is one of the small molecules. There are so many bigger molecules like your skin, your nails, like plastic. These are all much, much bigger complex molecules. And the simple molecule of caffeine itself is taking 10 to the power 48 bits to just model it in one fraction of a second. And the problem because for decades we have been simplifying nature into a string of zeros and ones. And that's a big problem because zeros and ones are not able to model nature. You can only simplify nature up to some level. If you try to simplify it too much, you can't model it anymore. And that's where the qubits come in. The qubits not only have zeros and ones, but they have both 0 and 1. And that property is called superposition. So I hope you have learned about these things in the past few classes that you took. I'm sure you also heard about entanglement. These qubits can share information jointly. Entangled qubits can share information. And the third is a property called interference, where interactions affect the likelihood of the solution, which means positive things get reinforced, negative things get attenuated. And these are the three special properties which allow the qubits to model nature. And that's the reason why modeling caffeine or your skin or plastic or whatever is much easier on a quantum computer. That is why, because of these properties, you can also do things like prime factorization. And because of these properties, you are also able to solve things in AI much more efficiently. Now, remember I told you, you can run your code using the same Python libraries. Same Python runs on quantum computer and on classical computer. But on a quantum computer, the algorithm you write to solve the same problem, the cat problem, for example, you would solve it on a classical computer in a different way. So those of you who do AI would know that you have multiple types of classifiers that you can build, and these classifiers you can run them using Python code, for example, right? Now on a quantum computer, you have to utilize these special properties, superposition, entanglement, interference, and that is how you're going to take that advantage, that special advantage of the qubits comes from using these properties. So the algorithm is different. The programming language is the same, Python, but the algorithm, the way you write it, the way you model it is going to be different. Okay. So I know you studied some of these things in the previous classes. So today I'm here to give you the broad overview. Okay, I'm going to give you the broad overview of where the technology is and what are you going to do next. Okay, that's my question to you, right? What are your contributions in this going to be? Because I'm going to paint the landscape for you. And in that you can say, that's where I fit, or that's where I fit. Okay. So that's the goal here. Okay. So our goal here is to write algorithms in a new way. But what this now means is that you have now got, for the first time in the history of computing has branched. Two different types of computers. On one side is your bits, your mobile phone, your laptop, your supercomputer, your GPU. All of these use bits as the fundamental unit of information. And for the first time, a new kind of computer is available, which is called the quantum computer. And this quantum computer, the fundamental unit of information is qubit. And that qubit, as I said, has these special properties. And hence, the quantum computer is not an extension of the classical computer. It's a very different kind of computer. So even though you can use the same programming language, the underlying compute is completely different. It is modeled and structured in a very different manner. So in future, what is going to happen? Three types of processors are going to be available to you. In fact, they are already available. The three types of processors are, one is the CPU, which sits on your laptop, mobile phone, and all these places. The CPU. Then comes the QPU. The QPU, usually there are some laptops with GPUs. The GPUs, usually they sit in servers on the cloud. So to run your AI programs, to run, for example, your chat GPT or something, you can't run it locally on your laptop. You run it somewhere else on a cloud where the GPUs. The third type of processor is the QPU, and the QPU also today sits in the cloud somewhere there. Okay. And you can access it, like I said, using Python programs on your laptop. Okay. So today, I don't know how many of you have actually used a quantum computer, but I'm going to at least tell you how you can use one so that by tomorrow, you can all say that I've used a quantum computer. So I have two homework for you. First homework is, at the end of this talk, I want all of you to go and start using a quantum computer so that tomorrow you can say, I went to this talk and I used a quantum computer. Okay, that's number one. Number two, I don't know, you all use Wikipedia, I'm sure. So on Wikipedia, can you please go to the Wikipedia page for anything related to quantum computing or quantum technologies and write one line there or change one line. You know, if you think somebody has written a wrong statement or something, or add something to it. So the point is, you're not here just to listen. You are here to go and act. After you have listened, for you to go and write one sentence on Wikipedia where you can put your knowledge, whatever you have learned, okay, whatever you have learned, use that and write one line on Wikipedia. Okay, so 2 homework items for you at the end of this talk. So we talked about Moore's law for classical computers, where the classical compute power has been doubling every almost 18 months to 2 years for the past several decades. In quantum too, we are seeing a similar exponential law. 2016, IBM put out a 5-qubit quantum computer on the cloud for the first time. That was 2016. 2024, there is a 156 qubit. And by 2033, we are going to have at least 1 lakh qubit. And also, the processor has been improving. The number of gate operations or the number of you can run. So think about the number of qubits and the number of gate operations as the allowed complexity of your code, or the bigger programs. You can run bigger and bigger and bigger programs. So I talked about prime factorization. So today you can prime factorize small numbers, but as the number of qubits goes up, as the number of gates go up, you can prime factorize bigger and bigger and bigger and bigger integers. Okay. And one day, of course, as I said, that 2048-bit integer also, once we have sufficient number of qubits and sufficient number of gates on the processors, we will be able to run larger numbers, right? So the point of this is that there is a development roadmap already in place, and that development roadmap is showing that quantum computing is also increasing in power very, very fast. And there is a Moore's law-like effect happening. So 2027, quantum computers, which is like, they will keep evolving, and error mitigation techniques are being used to reduce the errors. But for the first time in 2029, quantum computers will have error-corrected qubits. Okay, error-corrected qubits means that you can run your code much more efficiently. You can solve much bigger problems, and that's one big milestone which quantum computers are yet to cross, and that milestone is likely to come in the next few years. So we are in 2025. Another milestone is this milestone called quantum advantage. What is quantum advantage? Quantum advantage is the day quantum computers solve a business problem, a real problem from the world, a business problem where a quantum computer surpasses a classical computer either in terms of time required to do the processing, or the cost, or the efficiency. In all these parameters, once the quantum computer crosses, that's another big milestone, because that means that quantum computers can now achieve what they are potentially being said that they can show. So for example, that Shor's law, this molecular simulation, they are all projections based on mathematical mathematically proving that it is possible, right? But do we have a quantum computer that big to run these programs today? Not yet. But when do we have that to achieve this quantum advantage on certain problems? That year is 2026. So right now, which year are we in? 2025. So by next year, we expect that quantum computers on certain business problems will have actually shown that they are much better than classical computers, faster, more efficient, cheaper on certain tasks. Which are those tasks? People are actually right now working on this. Okay, so I'll again stop sharing for a minute just to see if anybody has. Okay, yes, very good. So we have a question. Ramakrishnan, yes, sir. Okay, do you have a question? Okay, anybody has a question? Okay, what about the chat? Let's just look at the chats. Okay, somebody has answered China. Okay, we'll go and see what the answer is. Okay, yeah, please feel free to ask. The goal here is for all of us to get better at this. It's a new technology. We all have to get better at this. And we can do that by asking each other lots of questions. Okay.
So what type of hardware changes we have to make to convert a classical computer to quantum computer? Can we assemble something, or what type of hardware involved? Sir?
Okay. So the classical hardware, we can't use it. Gone. Your classical computer can simulate up to about 20 qubits. You stretch it, it goes up to 30, 35 qubits, but that's it. Up to about 35 qubits, your bits can simulate. But beyond that, no, they cannot simulate. Okay, so gone. So which means your current classical technology cannot be used. You can't use it. So what do we use? We use particles which have quantum mechanical properties. So think of it. I have this bag in my hand. I throw it. Can I say where it will go and fall? Yes, if I know the direction. If I throw it this side, I know it will go and land that side. If I throw it this side, I know it will go and land this side. Depending on the force, I know how far it will go. Depending on the force, I know how far it will go. And that's classical, right? This object, big object, I'm able to predict things. Now I keep shrinking this object, make smaller, 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 and it becomes so tiny. One molecule, one electron, one photon, one small sets of molecules. Then what happens? I throw this small bag. Quantum mechanics says this particle will fill this room. It's everywhere, everywhere. It's all across the room.
But there
I
was
throw
only
it,
one
it's
computer.
everywhere. So that's quantum mechanics. And that's superposition. You cannot predict its position, mass, many things, but those are the tiny particles you need to do your computation in a quantum computer. So today there are multiple ways in which people create these qubits. Light is one, single photons, single light particles, electrons, neutrons, small molecules, ions, neutral atoms. So there are multiple techniques. Some of them are room temperature, Some of them have to be cooled to minus 273, close to minus 273 millikelvins. I mean, it's in millikelvins, the temperature. So these qubits today are created using multiple techniques. The one which is currently the most successful is called a superconducting qubit, which is kept inside a dilution refrigerator about 3-4 feet tall, where at the top of it, it is at around 40 Kelvin. At the bottom of it, it is at 0.1 millikelvin. Okay. So, sorry, 10 millikelvins. Okay. So that's and that's one of the leading qubit technologies. Okay. Where the qubit, the superconducting qubit is kept very cold, and that is then given pulses, and that does the computation. Yes, Vrushali Nikam.
Hello, sir.
Yes,
Am I
ma'am.
audible?
Yes, please go on.
Sir, can you suggest me something related to quantum image representation techniques?
Yeah, sure. So, quantum image representation today is not at all very efficient. Not efficient. So, you shouldn't be trying it, in my opinion.
Okay, sir.
You should be using. So, if you are doing some image processing, image classification, what I would suggest to you is to look for classical ways to extract your features, and then use those features, in a quantum computer where you are doing the classification using a quantum. Okay, so that's my suggestion. But of course, there are multiple ways in which you can go and try to do these problems. Okay, so yeah.
Thank you, sir.
Sure. So yes. So now let me then go back to the presentation. Okay. Please keep your questions coming. Let's keep asking more and more questions. Okay. Okay, so we want to reach quantum advantage. And so what is this quantum advantage? So I just told you it has to be the day when quantum computers become better. Have we seen advantage in other technologies?
Sir, am I audible?
Yeah, please go on.
I have one question. Actually, I'm working in the area of natural language processing. So I have read few papers where they have drawn the discocad diagram using the Lambda, and then they have converted that discocad diagram into the AND circuit. So can you tell me, are there any resources using that I can work on quantum natural language processing, especially for the regional languages? As there is I don't found any implementation kind of paper, or I found less resources using which I can proceed in that particular area.
Okay, so the other thing I want to tell all of you is that not every problem is good for quantum computers. Okay, so you look at, let us say, multiplication. Is multiplication faster on a quantum computer or on a classical computer? It's faster on a classical computer, several hundred times faster. Okay, so there are only certain problems which are good for quantum computers. Now, I'm not saying image processing or NLP is not a good problem, but what you should now look for are, on your classical processing, first of all, you have to take your classical processing to the limit. Say that, okay, let us say you are trying to solve some text classification, or you're trying to build some models for understanding natural language, whatever you're doing. Now, if, for example, that process is taking too much time, let us say it's taking 10 days to solve on a supercomputer or on your GPU or whatever. So now in the near future, what you should do is try and see, can you break that problem into pieces which are easy for the classical computer, and those problems which are hard for the classical computer, so that those parts you can try on a quantum computer. So don't try to do everything on a quantum computer. Try and do only those parts which you are not able to solve on your classical computer, and which then can be converted into quantum data. And that data can then be processed on a quantum computer much faster. So there are things which, for example, I talked about molecular simulation, I talked about factorization, I talked about certain types of machine learning. So there are some problems which are faster. And now, as I said, you take your classical problem, break it up into parts, see which parts are running well enough on your classical, which are the parts which are not running well enough on your classical. Take those parts, write that algorithm in a quantum way, see if you can write it. If you can, great. If you cannot write it, then it's not even a problem for the quantum. Okay. So at this point of time, there is a lot of discovery also happening to understand what are the problems which you can solve on a quantum computer and what are the problems you should not even try to solve there and just stick to your classical. Okay. So that's a long answer to your question, ma'am. But I think, you need to, first of all, understand what is that problem you are trying to solve. Is that even solvable on a quantum computer? And if so, how are you going to solve it? And what is that algorithm you are going to write, which uses superposition, entanglement, interference, and all these properties, which gives you that quantum advantage? Okay, so I asked you, where is all the quantum talent sitting? Okay. So there are many reports which are saying that quantum talent is actually sitting in India right now. And in fact, if you see even the online cloud quantum computers today, a lot of the usage is actually happening from India. Indians are the people who are using these quantum computers to a large extent. And this is a McKinsey report. As you know, European Union is several tens of countries put together. As a single country, India today has the maximum talent, okay, sitting in India right now. Okay, you're all part of that talent pool. And to tap this talent, Government of India has announced what is the National Quantum Mission, where they are giving 6,000 crores to do research, do technology development, all of these things in quantum computing and quantum technologies. So last year, the Government of India, Department of Science and Technology, under the National Quantum Mission, announced 43 institutions there was a call for proposals. There were 384 proposals from around India. 17 of those proposals were selected. These 17 proposals were spread out among 43 institutions. They had all pooled together. And these institutions in the first round were selected to receive that funding from the Government of India. And 4 hubs were selected: ISC Bangalore for quantum computing, IIT Madras for quantum communications, IIT Bombay for quantum sensing, and IIT Delhi for quantum materials. Okay, so these 4 hubs were built, and now the government is channeling that part of that 6,000 crores to these institutions. And in fact, your institution should also see how in the next few rounds your institution can participate. In fact, on 20th not 20th, 17th or 18th of August was the last date for a new call which DST brought out, which was for algorithms. So multiple opportunities. In fact, there is the Department of Biotechnology also, which has brought out a call. So for institutions like yours, there is now an opportunity to actually raise a lot of funding from Government of India. Crores of rupees money is being given by the Government of India. If you are willing to write good proposals, do good research, and build technology. So one aspect is this institutions. The second is the government is also supporting startups. So in the first round, 8 startups were supported by the National Quantum Mission. And those 8 startups, received funding between 1 crore to 25 crores each one of them. Okay. So a lot of money being given to startups, and a lot of these startups are actually being built by students and faculty coming together. So again, a big opportunity for all of you to actually come and think about what are those problems you can solve, what are those things you can build, whether in software, hardware, all of this, how can you do that and actually build technology, because as I said, India is where all the talent today is sitting. Okay, India is the talent pool, India is the talent hub, and the government of India wants to make sure that this talent is utilized in India for India to take the lead as a country. There is also a third thing which the Department of Science and Technology National Quantum Mission did, which is they announced 6 courses where a student of any branch, if they take 6 of these courses out of a total of 11 possible courses, if they take 6, doesn't matter which branch you are, civil, mechanical, computer science, electrical, electronics, whatever. If you do these 6, you also get a minor degree in quantum technologies along with your major degree. So this is the third piece of thing which the National Quantum Mission is doing, where the goal is to make sure our talent pool is the biggest, continues to be the biggest, and our talent pool in this country builds startups, builds industries, builds the technology which is going to make us a developed nation going forward. So the answer to the question which I asked you was not US, not China, it was actually India. So I'm again going to stop for a bit and see if there are any questions.
What is the eligibility criteria for these courses, sir?
Eligibility criteria for?
One of these courses you just showed us.
Oh, the eligibility is you just need to be, the student needs to be a first year set. So 6 courses need to be offered by the institute, and the institute has to decide when to offer it to the students. And as I said, at least AICTE wants these to be open to all the branches. So you need to have your faculty to take these courses, and in fact a lot of FDPs are going on across India now, where they're actually training teachers to conduct these courses and ensure that you are able to teach these courses to the students. And as I said, 6 of these courses, there is an option of 11. So if you go to the AICTE website, you will see that there are 11 total courses, out of which any institute has to pick 6 of them. Okay, and those 6 need to be offered over a period of 2 to 3 years. And students who complete 6 of these courses will get this minor degree.
Thank you, sir.
Okay, sir. Thank you. Okay, I'll go back. Okay, so now going forward, so there are, as I said, I talked about 3 examples, so what we are now going to do is look at more examples of what all things can you do with quantum computers and what are the things people have already started doing. Okay, so one example is protein structure prediction. So do all of you know what were the 2 Nobel Prizes? What was the Nobel Prize in physics for last year? The physics Nobel Prize was for AI.
Is it for quantum entanglement, sir?
No, the last year's physics uh, entanglement one was the previous 2022, I think. You're right. It was 2022. But the 2024 physics Nobel Prize was for AI, the founders of AI.
Jeffrey,
Yes, Hinton and the other person. Yes.
John.
Many people don't know that actually the chemistry Nobel Prize was also for AI. The chemistry Nobel Prize was for protein structure prediction using AI. So these people had found ways to, so in your body, there are about 25,000 to various estimates exist. There are multiple proteins in our body. Okay, so multiple proteins are there. And for example, what is disease? Disease is a protein which is shaped like this becomes like this, for example. This is disease. Okay. Now, what is medicine? Medicine is something which comes tick, 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 fixes the protein. That is medicine. Okay. So, finding these medicines, which are typically molecules. Now, remember, molecules you cannot model on classical computers. Remember caffeine. Your medicine molecules are even bigger than that. Okay. So, these molecules, you're not able to model them. So hence what you do is, your protein and your molecule, you have to try them out in test tubes. But last year, the Nobel Prize in chemistry was for people who said that given the protein, the amino acids that it's made out of, I can now predict its shape. How will it be? Will it be like this? Will it be like this? Will it be like this? Whatever. What is the shape going to be? Now, here in this work, the IIT Madras and IBM team, what they did was they looked at protein structure prediction for unseen molecules. So AI, as you know, is good when you give it examples. But something new comes, it's not able to generalize well. AI is not able to. So you train it on cats, it will recognize cat. But as soon as lion comes, it doesn't know what to do because that's something new. And that's where quantum helps. It is able to help in this protein structure prediction problem, especially for new structures. Okay, structures which are not there, for example, in your training data set. So there are multiple such examples in chemistry, physics, and all these. And the kind of generally what are the problems that people are today solving using quantum computers, or at least trying to solve, like ma'am asked this very nice question about, can I solve NLP? Can I solve image processing? So people are right now trying to figure out what are those problems which I can solve and achieve quantum advantage. So in banking, people are trying to solve fraud monitoring, portfolio optimization, risk simulation. In automotive, people are looking at how do I design new battery materials? How do I design new materials for the body of the car or the rocket or the submarine or the torpedo or our Agni missile all of these, how do you find better materials which are more heat resistant, which are able to go longer distances because they might be lighter? So all these properties, like wherever there is chemicals, life sciences, healthcare, logistics, so across multiple such domains, people are now looking for those use cases which they can try and solve, which is going to help us in doing better than a classical computer. Okay, so I told you quantum advantage. Where is quantum advantage going to come from? It could come from one of these use cases. Okay, and people are trying to solve all these use cases. The three main types of problems which people are, we are today able to solve. One is simulating nature. So remember the caffeine molecule. Second is mathematics and processing data with complex structure. So things like cat, how do you represent it? How do you solve that? How do you do the factorization? And the third type of problem is search and optimization. That's the third kind of problem which people are today trying to solve. And these are across these domains like automotive, financial services, high-tech areas, and multiple such areas. People are now using quantum computers to try and solve these problems which are across these multiple domains. Okay. Any questions? So, sir had asked this question about how do I make these quantum computers? Okay, so before we go there, in your laptop or in your mobile phone or almost any electronics, today 5 countries are controlling the supply chain: China, US, Taiwan, South Korea, and Japan. India is not there in any of this. We don't control the global supply chain for any of the electronics today, whether it is in hardware, whether it is in software, whether it is in middleware, none of those. Okay, so we don't do that. But the whole national quantum mission is about how are we as a country going to control this supply chain going forward. The supply chain of a quantum computer, which something looks like this. This, as I said, is a very cold fridge, which is where the quantum processor is kept. And there are multiple such electronics inside, things like, microwave sources, microwave signal generators, amplifiers, the processor itself, a lot of the wiring. Remember, these are very cold temperatures. And at those temperatures, you want to be able to, do your, your signals need to be passing through the wires. So all of this needs to happen. And all of these components also need to be made for the quantum computer. Okay. So one of the goals is for India to, of course, look for algorithms and software applications which we can solve, which I talked about in finance, logistics, optimization, and all those areas, but also in this hardware area, where can we build some of these components, and in future, can we control parts of the supply chain, which today we don't do at all in the classical computer. Okay. So that's one of the other goals. So for you as young people, there are multiple opportunities to work in software, algorithms. There is also an opportunity to work in the hardware domain. And there are multiple job opportunities today opening up. These jobs are there, for example, in fact, in my team in IBM, we are right now looking for BTechs, MTechs, PhDs, all of them. People who are good at mathematics and quantum mechanics, but who also know how to build a system using Python, Rust, programming. You need to be excellent at programming also to be able to take your ideas and build something out of it. The hubs which I talked about, I showed you this map of India. Each of these institutions which I showed you is now starting to hire people for as junior research fellows, senior research fellows, postdocs, PhD students, master's students, in fact, faculty. They're also looking for, in the hub, they're looking for CEOs and CTOs and various things. And remember, I also told you there are the startups which are getting funded. These startups are also now looking for people who can come and start solving problems. Okay. So for you now, there are multiple job opportunities which have opened up in the quantum area. Each one of you, depending on your interest, depending on what kind of, skills you possess, you can come into the software area, the algorithms development. You can also do the hardware, multiple parts, as I said, depending on what, if you're good at physics, you could be looking at the processor or the amplifiers or things. If you're good at electronics or electrical engineering, there are other parts you can look at. If you're good at control systems, you should be looking at other things. So there are multiple job opportunities today in India and of course across the world. There are studies which show that there are several open positions, but people are not there to fill those positions. Okay, so here is an opportunity for each one of you, and please don't go and solve toy problems. Solve real big problems. Solve problems where you are, for example, contributing open source packages like Linux, like Qiskit, like PyTorch. Pick something and contribute to open source so that you are working with the best in the field. You need to, today AI writes all the programs for you. You don't even have to write programs, but you need to be able to, if somebody gives you a use case, you need to be able to very quickly go find the tools and write the code and build your system. Okay, it should be very simple now, because it's almost like, like if you had to make a sabzi, the recipe is there: cut brinjal, put it in the tawa, add salt, add oil, mix it up. Same way, you go to YouTube, you'll find so much very good content from everywhere. And it's very easy for people to now go and build these things. So in fact, in the job market, it is not enough to just say that, oh, I did my BTech here, I got 9 point whatever CGPA. No, you need to have actually built these things, and you need to have contributed to open source and various other things where, your GitHub, for example, should be very active with a lot of commits and various, all your code put there and all of that, right? So you need to now become more hands-on, very much, where you are actually building systems. In the hardware area, it's much harder because the hardware labs are there only in some of the very few big institutions of India. But on the software side, it's all open source. You can start going and contributing. You just need to become very good at languages like Python, Rust, C, C++, whatever. It depends on which package you have picked. Okay. But you need to become world class, and you can very easily do it today using all the learning material that you are getting from your professors and also from open source and YouTube videos and all of that. Okay, so I'm going to, I told you today 2 homework I gave you. The first homework, please go to IBM Quantum, create a sign-in and start using a quantum computer today. Okay, it's very simple. Just go and do it. You can start doing it today. Tomorrow you can say, I'm done. I can use a quantum computer. Please do that. There is also a website called IBM Quantum Learning, where you can go and start taking free courses. It will tell you if you are a beginner, it will give you beginner courses. If you are intermediate, it will give you intermediate courses. So you can basically pick the kind of courses you want. You can also earn badges and various things which you can put on your LinkedIn and places. And IBM is not the only one offering courses. You will find them everywhere. Okay, so lots of them. But when you learn, please also go and do projects, because it's very easy to think, oh, I did 5 courses, now I'm an expert. No, sorry, you're not an expert until you have built something. Okay, so you need to go and start building. You need to in today's world, it doesn't matter whether you're doing physics, chemistry, biology, or you're doing electrical engineering or computer science, but you need to be excellent at programming, because all you need to be is an architect. The agents and the co-pilots and all will do the programming for you. So please, please, please pick up programming languages, build things. Okay, it doesn't matter what thing it is, but you must have, if somebody says, can you build a chat GPT for your college, I will give you all the documents which are there. For example, maybe all the student records, and give you everything there. Can you build a chat GPT on top of that? You should be able to do it in 2 days. Okay, so those are the kind of things you need to be good at to get into the job market today. Everything can be done in a week's time today. Okay, so you can go learn, start, but with the learning, also start building. Okay, right now. So I will again stop, take questions. Please ask questions.
Is the courses are free?
Yes, lots of free courses. There are courses on that IBM Learning platform. Then there are NPTEL courses also, which are free. You know about the NPTEL program. Lots of free courses everywhere. There are many, many, many free courses. Please just go and take them. They, take simple courses, but don't only keep taking courses. Start using that knowledge which you learn to build things. Go and start building on your laptop, on your computer.
Okay, so thank you.
Yes, Qiskit is free. Qiskit is an open source. And in fact, for all of you, I would actually suggest, don't be a user of Qiskit, but a builder of Qiskit. You know what open source is, right? Open source means that you can actually go and write the libraries, the functions, and all of that. It is like Wikipedia. Most people just go and use the Wikipedia, but you should know that you can also write in Wikipedia. You can create a page for yourself. You can become a celebrity by creating a page for yourself on Wikipedia. Of course, somebody might come and say, no, you're not a celebrity, please delete your page. But it is community driven. If the community says, yes, you are a famous person, then yes, you are a famous person. And that's how Wikipedia works. Same way, all the open source programs like PyTorch, Linux, Qiskit, they're all open source. You can actually go and contribute to them. And once you start contributing at that level, it means you are world class. Okay. So every student should aspire to be world class. You need to become the best, and to actually not just be users of Qiskit, but writers of Qiskit. You need to be the person who is, and to begin with, or you can just go and look at correcting errors in the documentation. Many of the today's star programmers on some of these open source packages started out as people who fixed bugs and errors on the documentation, not even on the code side, on the documentation. Then they slowly, tried more and more and more, and became better and better, and solved. And today they are, star contributors to some of these things. Okay, quantum technology as PhD research area. What can be possible approach? Okay. If your institute has a very good physics lab, if your institute has very good lab facilities, then you should start doing hardware if you can, right? So for hardware, you need things like I said, you know, you need a dilution refrigerator, various things. So if your interest is in hardware and your institute does not have, for example, let me say it doesn't have, for the sake of argument, then if you are interested, please go and visit IIT Madras. Go and visit those 47 labs which I told you. That map is available online. You can easily find it. Find some professors there. Ask them, sir, can I come for 10 minutes? Ma'am, can I come for half an hour to your lab? Please just show me around. Please put some effort. Today, you know, you can all send emails, LinkedIn, whatever. It's very easy. So on the hardware side, if you have a lab, great. If you don't have a lab, have an aspiration to get to that lab. You know, it could be one of the 43 institutions. They're all setting up labs, and you can then figure out which part of it. But the software side or the algorithm side doesn't need any of that. You can use on the cloud. I just showed you how you can access a quantum computer. So it's very easy for anybody to go and start using these quantum computers on the cloud. Okay, so that's something you can do. So as a PhD, for your research, the hardware side is also open, the software side is also open. Then if it is sensing, materials, communication, computing, various verticals are also open. So you can now pick based on your own interest, what and the kind of lab facilities which are there, or your aspiration, which IIT or which ISC or ICER or which BITS or what you want to join, which has these labs. I think you should plan it like that, because that's the best way for you to do. And as I told you, the jobs are plenty. If you become very good, you can go anywhere you like, to the best institutions in the world, including IIT, MIT, this one, that one, everywhere you can go if you become that world-class person. And to become world-class, as I said, it's not very hard. You need to have that path. You need to find those avenues and get there. Okay, any other questions? Sir, but I tried and it gave 10 minutes. Yes, 10 minutes. But that 10 minutes is, ma'am, okay. That 10 minutes is QPU time, okay. That QPU time, you show me your program, okay. If it runs for much more than a few milliseconds, I'll be very surprised. Most programs that we write run in a few milliseconds, okay. So even to finish that 10 qubit, you need to be a power user, a good user. You need to have a very big problem that you are solving. So I don't know which problem you are solving, but that 10 minutes is usually very, very sufficient to do many of the things that people do. But if you have finished your 10 minutes and you need more, then okay, please contact and we will see, you know. And that's where the National Quantum Mission is actually looking for people like you who are able to finish your 10 minutes and still your problem is running. That means you have a real big problem, and that's something worth solving probably. So there are multiple ways for you to access, you know, more time on these quantum computers. I hope that answers your question. Yeah. For exploring and all, that 10 minutes is QPU time. I will be very surprised if you finished it. Okay, QKD, I don't know much. Okay, I don't know which all simulators you can use for QKD. I'm more on the computing side. Okay, quantum computers. So for QKD, you will have to ask somebody who is working in the QKD area. Okay, so I think there are no more questions. So I'll just, if you put 100 disks on towers of an eye, will it solve? Okay, so that's a good question. So right now, the kind of optimization problems that quantum computers solve is no better than what you can solve on a classical computer. Okay, so something you can't solve on a classical computer, you can't solve on a quantum computer today. But those are the algorithms that people are searching for. Okay, can you find those quantum algorithms which will solve problems? And that's the quantum advantage which I talked about. Okay, so quantum advantage is where you are able to solve optimization problems, problems of search, problems of these, fitting. How do you solve them on a quantum computer much more efficiently? And that's where the world is searching. And that's where I said quantum advantage is likely to come on a certain set of problems by 2026. So there are multiple opportunities for, doctorates in this area. But like I said, a doctorate needs to have hands-on experience. If you are in the hardware, there should be things that you can build. There should be things that you can do experimentally. If you are on the software side, then you need to be finishing those 10 minutes and crossing into multiple minutes. And you have to have a big problem which you are solving using multiple qubits and multiple gates. So if you are reaching those levels, then there are multiple opportunities. Like I said, everyone is looking out for you. As I said, technology companies, including IBM, then the National Quantum Mission, those labs are looking for you. The startups are looking for you. So all of these people are looking for your things. Okay. Requesting you to share your email ID. Yes, sure. Yeah, I shared. Yeah, so I've shared it. Okay, so I think we are running out of time. So if there are no questions, we will stop here.
Thank you, sir. We had a great opportunity to listening to you, and really the talk was fascinating, opening up a lot of opportunities for us to the faculty community. That's why we wanted you to talk on what actually India is going to do and what India is doing on that. Thank you, Dr. Venkateswaran. Thank you very much.
Thank you. Thank you.
Even we are
I'm very happy that you are conducting, FDPs and programs like this for faculty and, for especially, because this is the community which is going to really drive our national quantum mission. So each one of you now needs to, go up that level where you become hands-on. You are trying to solve problems and also pushing your students to solve some of these tough problems.
sure, sir. Naturally, we'll be on that mission. We'll join you, and we are looking forward to interact with you to take our institutions to the expectation of India. Thank you, sir. Thank you very much.
Thank you. Bye. Bye, everyone.
Bye, sir.
Thank you, everyone. With this, we conclude the day 3. And tomorrow on day 4, we have session 7 by Dr. K. Sethuraman and session 8 by Dr. A. Bashiruddin Muhammad. I'll see you all at 6 p.m. tomorrow. Have a good night.